Welcome to Night Cosmos Sleep. For most of human history, objects arriving from beyond our solar system existed only in speculation. The space between the stars is unimaginably vast, while the fragments of rock and ice drifting through it are far too small and too dark for us to detect easily. They could pass through the sun's neighborhood and continue on into the darkness without leaving behind any clear trace. But every so often, a visitor like this comes close enough for its light to reach telescopes on Earth. At first, 3I, Atlas, did not appear to be anything spectacular. There were no sharp images of a frozen world and no chemical signatures yet revealing its ancient age. Everything began with a faint point of light, almost indistinguishable from the countless other points that seemed motionless against the sky. Only when that point of light began to move did the story start to change. By comparing images taken at different times, astronomers traced its path, calculated its orbit, and gradually realized that this was not an ordinary comet traveling around the sun. It was passing through our solar system, on a journey that would happen only once, carrying material from a place beyond the familiar region of space we call home. Before the layers of ice on 3I, Atlas were analyzed, and before its isotopes revealed a past that may stretch back tens of billions of years, there was one very simple moment. The moment humanity noticed a tiny point of light moving in a way it was not supposed to move. In early July 2025, a faint point of light began attracting attention within data collected by the Atlas survey system. Atlas is the abbreviated name of a network of automated telescopes built to continuously monitor the sky. Its primary mission is to search for small objects that may approach Earth, especially asteroids and comets whose orbits need to be identified as early as possible. The Atlas telescopes do not observe the sky in the way a person might look at a single star through a telescope. Instead, they photograph broad regions of the sky at different times. Computers then compare the images, searching for any point of light that has changed position. Most stars are so far from Earth that, over the course of several minutes, several hours, or even several nights, their positions in the images appear almost unchanged. They create a stable background, like dots fixed in place on a map. A nearby asteroid or comet behaves differently. As it moves through space, its position against the background stars changes. In the first image, it may appear beside a faint star. In the next, it may have shifted by a small distance. By the third image, that movement may form a path clear enough for the system to recognize that it is not a stationary source of light. The object later named 3I, Atlas first appeared in exactly this way. It did not arrive with a long tail stretching across the sky, nor was it large enough for telescopes to reveal its surface or true shape. In the earliest data, it was only a faint dot among countless other points of light. From a single image, it would have been almost impossible to know what that dot was. It might have been a dim star, a small disturbance in the detector, or a source of light at a much greater distance. But when several images were placed beside one another, the point began moving away from its original position. The shift was slow, but orderly. It was the first sign that a real object was traveling through the region of space near our solar system. After the initial discovery was reported, other observatories began pointing their telescopes toward the same part of the sky. Every new measurement provided another position. These points were like small markers placed along an unfinished road. One point revealed where the object was at a particular moment. Two showed the direction in which it had moved. But to understand its complete motion, astronomers needed many more positions collected over multiple hours and nights. As the period of observation grew longer, they could begin estimating its speed, direction, and the way the sun's gravity was bending its path. This is why the following nights of observation were so important. An orbit is not directly visible as a glowing line already drawn through space. It must be reconstructed from many separate measurements. Every time a telescope records the object's position, another small section of its path is added. Once that path becomes long enough, scientists can compare it with possible orbits that follow the laws of gravity. At first, a short arc of motion may fit several different possibilities. The object could be nearby and moving slowly, or farther away and traveling much faster. Even extremely small measurement errors can change the estimated orbit. Time helps reduce this uncertainty. Night after night, the object continues to move. Its path gradually becomes clearer. The calculations are updated, and an unusual characteristic begins to emerge. It was entering the inner solar system with a speed and direction unlike those of objects that had long been held by the Sunday. To verify the result, astronomers did not simply wait for new observations. They also returned to older archives, searching for images taken before the date of the official discovery. Survey programs record the sky almost continuously. Hidden within those images may be many objects that were never noticed, simply because no one knew exactly where to look when the pictures were taken. Once researchers had a preliminary orbit for 3I, Atlas, they could calculate backward and determine where it should have appeared during the previous days or weeks. They returned to the older images, examined the predicted regions, and found matching faint points of light. These pre-discovery observations extended the known path of the object. Instead of having only a few days of data, astronomers now had a much longer period over which to follow its motion. Every old position that was recovered was like a puzzle piece that had been lying inside the box all along, even though no one had previously known which picture it belonged to. As all the points were connected, the shape of the orbit became increasingly difficult to explain as the ordinary path of a comet belonging to our solar system. Familiar comets can travel extremely far away, sometimes taking thousands or even millions of years to return. Even so, they remain gravitationally bound to the Sunday. Their paths may be extremely long and stretched out, but in principle, they are still closed orbits. After passing near the Sun, they gradually slow as they travel outward and eventually return. The new point of light did not appear to be following such a path. Calculations showed that it carried enough speed to escape the Sun's gravitational hold. It had entered the solar system from interstellar space. Its path would be bent for a time by the Sun's gravity, and then it would continue outward again. It had not arrived to orbit our star. It was only passing through. This conclusion was not based on the object's color or shape. At such a great distance, the earliest telescopes could not see it as a distinct world. The most important evidence was its motion. A distant star may appear brighter or dimmer, but during short observations, it remains almost fixed against the sky. A smaller, closer object moves more noticeably, and when that motion is followed for long enough, its path can reveal whether the object is gravitationally bound to the Sun or merely passing through the region controlled by our star's gravity. For 3I, Atlas, its path provided the first evidence of its origin. The object's name also came from that conclusion. The number 3 indicates that it is the third confirmed interstellar object ever discovered. Before it, humanity had identified only 2 visitors from beyond our solar system. The letter I comes from the word interstellar, meaning existing or traveling through the space between stars. The name Atlas records the survey system that discovered it. So 3I. Atlas is not a name describing the object's shape. It is more like a brief note, marking its place in the history of astronomy. The third interstellar visitor, discovered by Atlas. Behind that simple designation lies a much larger meaning. For billions of years, planetary systems may have been continuously ejecting fragments of rock and ice into space. These objects drift between the stars, but most are far too dark and distant for humanity to notice. Only when one of them happens to pass close enough to the Sun does it become illuminated and turn into an observable target. No one knows how many similar visitors may have passed through our solar system before humanity developed surveys sensitive enough to detect them. Many objects may have quietly entered and departed without leaving any trace in the history of observation. 3I. Atlas was not seen because it stopped or transmitted some unusual signal. It was seen because telescopes happened to be observing the correct region of the sky at the right moment, and because enough images were taken for its tiny movement not to be overlooked. A faint point of light separated itself from the background stars. Other observatories then continued following it. The measurements became increasingly precise. Its path grew clearer, and an object that had initially seemed ordinary began to reveal itself as a fragment of material from another star system. At that stage, scientists still did not know what was hidden within its ice. No one could yet say at what temperature it had formed, during what era it had been created, or how long it had wandered between the stars. Its most important chemical secrets remained beyond view, preserved within material that was gradually approaching the Sunday. But its interstellar origin had already begun to emerge from the numbers, not from a spectacular image and not from an artificial signal, but from a curve reconstructed from many small points collected across many nights. Against the immense sky, 3I Atlas remained nothing more than a very faint point of light. Yet from the moment its orbit was calculated, that point no longer resembled any familiar comet. What captured the attention of astronomers was not its shape, but the path showing that it had never truly belonged to the Sunday. When the first recorded positions of 3I Atlas were connected, astronomers did not see a perfectly straight line. Like any object entering the Sun's region of influence, its path began to curve under the force of gravity. But that curvature did not mean the object had been captured. What mattered was the overall shape of the orbit and the speed the object already carried before entering the inner solar system. To be here this, we can imagine the solar system as an enormous gravitational valley. The sun lies at its deepest point, while the planets travel along paths around the valley's slopes. Earth, Mars, Jupiter, and the other worlds do not fall directly into the sun because they are also moving sideways at tremendous speeds. Gravity continuously pulls them inward, while their motion continually carries them to the side. The result is that the planets follow repeating orbits around the central star. These are closed orbits. They may be nearly circular or stretched into long ovals, but their paths eventually return to where they began. Earth completes one orbit in a year. Jupiter takes nearly 12 years. Some comets need tens, hundreds, or even thousands of years to return to the region near the Sun, but they still belong to the same gravitational system. No matter how far outward they travel, they do not have enough energy to escape the valley. In the case of a comet with an extremely long orbit, a person may see it only once in an entire lifetime. This can create the impression that it appears and then disappears forever. But if its orbit remains closed, the object has not truly left the solar system. It is simply continuing along an enormous arc, slowing as it travels outward, and perhaps returning after an interval so long that many human generations could never wait to witness it. The path of 3I Atlas is fundamentally different. Measurements gathered across many nights showed that its orbit is hyperbolic. In mathematics, a hyperbola is a particular type of curve, but here it is enough to understand that the path does not close. Its two ends continue outward instead of bending back and joining together. The object enters from one region of space, passes through the area near the Sun, and leaves in another direction without completing a single orbit. The difference between an extremely long orbit and an open orbit may look small in a diagram, but their physical meanings are completely different. An object on a closed orbit remains gravitationally bound to the Sunday. It may travel so far away that the central star becomes only a point of light, but gravity will eventually slow it down and draw it back. An object on an open orbit is different. As it continues outward, its speed never falls low enough to force it to return. It retains enough motion to escape the Sun's gravitational hold. The boundary between these two cases is connected to the idea of escape velocity. This is the minimum speed an object needs to leave the gravitational pull of another body without requiring any additional push. Escape velocity is not the same everywhere. The closer an object is to the Sun, the faster it must travel to escape. Farther away, gravity becomes weaker, and the required speed becomes lower. A spacecraft leaving Earth must reach sufficient speed to avoid falling back to the planet. In the same way, an object leaving the solar system must carry enough energy to climb out of the sun's gravitational valley. Most native comets do not cross this threshold. They move rapidly when they approach the sun, but much of that additional speed comes from falling deeper into its gravitational field. As they travel outward again, they gradually lose the speed they gained and are eventually drawn back. 3I. Atlas did not begin its journey in the distant solar system before falling inward. It was already carrying considerable speed before it entered the region where the sun's influence becomes strong. That motion came from its journey through interstellar space. As it approached, the sun's gravity accelerated it and bent its path more sharply. After passing its closest point, the object began slowing again as it moved outward. But even after the temporary acceleration provided by the sun was taken back, it still retained enough speed to continue leaving. We can imagine a stone thrown across a valley. If it moves too slowly, it will roll downward, climb partway up the opposite side, and then return to the bottom. If it has the right speed to move around the valley in a stable orbit, it will continue repeating its path. But if the stone arrives from far away with enough speed, it can descend one side, pass through the deepest region, and climb the other side without ever returning. The sun may alter its direction, but it cannot keep it there. That is what is happening to this interstellar visitor. The sun's gravity is not weak. It is strong enough to bend the object's path significantly and change its speed throughout the encounter. But gravity does not act like an automatic hook that captures everything passing nearby. Whether an object is captured depends on its energy, speed, and direction of motion. In a system containing only the Sun and 3I Atlas, it would be very difficult for the object to naturally lose enough energy to become a permanent member. Gravity accelerates it as it approaches and then removes nearly the same amount of speed as it departs. To be captured, it would need some mechanism capable of dissipating energy, such as a special interaction with a large planet or another object. Current observations do not indicate that such an event occurred. Its path therefore remains open. This orbit also explains why the encounter with 3I Atlas lasts for such a brief period compared with the object's complete history. It may have drifted between stars for an unimaginably long time, yet only during a tiny portion of that journey does it come close enough to the sun to be illuminated, heated, and made easier to observe. Telescopes have only a limited window in which to study it before the distance grows and the faint point of light becomes too dim. After leaving the inner solar system, 3I Atlas will not return according to any cycle humanity can wait for. It will continue beyond the region of the outer planets, travel far past Neptune's orbit, and gradually return to the cold darkness between the stars. Behind it, the sun will shrink from a bright disk into an ordinary point of light among countless other stars. Saying that the object will leave the solar system does not mean there is a clear boundary it will cross at one exact moment. The sun's gravitational influence extends extremely far and does not end abruptly. It simply becomes weaker with distance. Other stars and the overall gravitational field of the Milky Way begin to play relatively larger roles. 3I Atlas will never stop feeling the sun's gravity completely, but that gravity will no longer be strong enough to force it to return. What is remarkable is that the conclusion about its interstellar origin does not depend on what the object looks like. In the earliest images, it may resemble only a faint comet surrounded by gas and dust. As it approaches the sun, ice on its surface warms and releases material, producing the familiar features of cometary activity. From a single image, without knowing its path, it would be extremely difficult to recognize that it formed in another star system. An object can look entirely natural, display familiar activity, and still have a foreign origin. In the same way, an object that appears unusual does not necessarily come from outside the solar system. Appearance reveals how matter is responding to light and heat. The orbit reveals how the object arrived and whether the sun has enough gravitational influence to keep it. For this reason, the first and clearest evidence of the interstellar nature of 3I Atlas does not lie in its ice, its color, or its brightness. It lies in the positions recorded over time. When those points are used to reconstruct its motion, the resulting curve remains open. Its original speed is too great, and its direction shows that it entered the sun's region of influence from interstellar space. This does not mean astronomers can immediately identify the star system where it was born. Over long periods, both the object and the stars move around the Milky Way. Small gravitational influences accumulate, making it extraordinarily difficult to trace a path backward across millions or billions of years. Its current orbit tells us that it does not belong to the sun, but it is not enough to reveal precisely where it once belonged. Even so, the first important answer has been found. 3I Atlas is not a comet from the outer solar system completing an extremely long orbit. It is an object that arrived from interstellar space, passed through the sun's gravitational region, and will continue outward. This encounter is not the return of an old member, but the brief passage of a visitor that never belonged here. During this short encounter, the sun cannot hold it, but the light and heat from our star can cause the object's frozen layers to become active. In this way, 3I Atlas begins revealing part of the material it carried from another planetary system. Its open path explains why it will come only once. The substances later released around it may help answer a more difficult question. Where was this visitor created, and from what era did it come? But this is not the first time humanity has seen an object traveling along such a path. The two earlier encounters prepared us very little and left behind a great many questions. Before 3I Atlas appeared, humanity had confirmed only 2 occasions when an object from another star system passed through the region of space influenced by the Sunday. Those 2 encounters occurred less than 2 years apart, yet each object left a very different impression. One showed almost none of the familiar characteristics of a comet. The other appeared with a much clearer envelope of gas and dust. Together, they helped astronomers begin to understand that interstellar visitors do not necessarily resemble one another, just as the worlds within our own solar system were not all created from a single design. The story began in 2017, when a small point of light was discovered moving rapidly through the solar system. Its orbit showed that it was not being held by the Sunday. It had arrived from interstellar space and would continue outward after its brief encounter. The object was named Oumuamua, a Hawaiian word commonly understood to mean a messenger or the first visitor arriving from a distant place. Oumuamua became the first interstellar object ever confirmed. That fact alone made it an extraordinary discovery. For the first time, humanity knew with certainty that a fragment of matter formed beyond our solar system had passed close enough to be observed by telescopes. It was no longer merely a possibility predicted by models. It was a real object moving through a region of space that humans could measure. But the encounter was recognized too late. By the time Oumuamua was identified, it had already passed its closest point to the sun and was traveling away. Telescopes had only a short period in which to observe it before the object became too faint. The images did not reveal its surface or show its shape directly. Astronomers had to infer its form from changes in brightness as it rotated through space. The brightness of Oumuamua rose and fell dramatically, suggesting that it may have had an unusually elongated or flattened shape. But its exact form was never clearly seen. Descriptions of it as cigar-shaped or disc-like were interpretations based on the brightness data, not photographs that directly captured its true structure. What made Oumuamua even more difficult to understand was the absence of a clear cloud of gas and dust like those commonly seen around comets. Comets usually contain a mixture of ice, dust, and rock. As they approach a star, the light warms their surfaces. Some types of ice do not need to melt into liquid before becoming gas. They can change directly from a solid into a vapor. This process releases material into the surrounding space, sometimes carrying tiny dust particles with it, and creating a faint glowing region around the solid nucleus. This diffuse cloud of gas is known as a coma. It can be imagined as an extremely thin mist forming around the comet's nucleus. The coma may extend thousands of times farther than the nucleus itself, and is often the part most clearly visible to telescopes. As the gas and dust are pushed away by sunlight and the stream of particles flowing from the sun, they may form a long trailing tail. Oumuamua showed no prominent coma. Even so, its trajectory appeared to include a small change that could not be explained by ordinary gravitational effects alone. One natural explanation was that the object may have been releasing gas too weakly, or in a form too difficult to detect. The escaping gas could have produced a tiny thrust, enough to slightly alter the orbit without creating a bright cloud of dust like those seen around familiar comets. Because the available data was limited, no single explanation was immediately accepted by every researcher. Many natural models were proposed, ranging from a fragment rich in highly volatile ice to a porous structure altered by a long journey through space. The lack of information made Oumuamua both important and difficult to understand. It proved that interstellar visitors truly exist, but it departed before humanity could clearly determine what it was. 2 years later, another visitor appeared. This time, it carried more familiar signs. The object was discovered in 2019 and was later named 2I Borisov. The number 2 indicated that it was the second confirmed interstellar object, while Borisov was the name of the person who discovered it. From the earliest observations, Borisov clearly displayed the activity of a comet. A faint envelope of gas and dust surrounded its nucleus. As it moved closer to the sun, more material was released, creating a more familiar appearance than that of Oumuamua. Its orbit showed that it had arrived from beyond our solar system, but its outward appearance resembled some comets that had been known for many years. This provided an important lesson. An object from another star system does not necessarily need to have a strange shape or behave in a completely unfamiliar way. The processes that create comets may occur around many stars. In the cold regions of a young planetary system, ice and dust can gather into small bodies. Later, gravitational interactions with planets or passing stars can throw them outward. Some of those objects then begin their journeys between the stars. Borisov allowed astronomers to observe an interstellar comet more clearly. The gas escaping around it could be analyzed through spectroscopy, a method that separates light into different wavelengths to identify the signatures of molecules. Although humanity could not fly to the comet and collect a piece of its ice, the light coming from its coma still provided information about the material being released from its surface. But Borisov also served as a reminder that every opportunity has its limits. Astronomers could observe only the substances released during a certain stage of its journey. The nucleus remained far too small and distant to be seen in detail. The object continued moving and gradually faded as it left the region warmed by the Sunday. Like Oumuamua, it left behind only a brief window of data before returning to the darkness of interstellar space. The first 2 encounters created almost opposite impressions. Oumuamua showed little obvious cometary activity and forced scientists to draw conclusions from extremely faint clues. Borisov displayed a much clearer envelope of gas and dust, allowing its composition to be studied more directly. One object raised questions about shape and motion. The other created an opportunity to investigate the chemistry of a comet formed beyond our solar system. This difference also showed that interstellar object is not the name of one specific type of body. The term describes only an object's origin and path. An interstellar object could be an ice-rich comet, a relatively dry body of rock, a fragment broken from a planet, or a small celestial object with a structure unlike anything humanity has encountered in our solar system. The most important feature they share is an orbit that is not gravitationally bound to the Sunday. For this reason, the terms interstellar object and comet should not be used as though they mean the same thing. A comet is identified mainly by its abundance of volatile materials and its activity when it approaches a star. An interstellar object is identified by a path showing that it arrived from beyond our planetary system. A comet can be an interstellar object, but an interstellar object does not necessarily have to behave like a comet. By 2025, 3I Atlas had become the third known visitor. This time, the situation was different from what it had been in 2017. Astronomers had a clearer understanding of what needed to be observed. Survey systems had improved. Many telescopes on the ground and in space could work together to track the object's orbit, brightness, dust, and surrounding gas. Instead of recognizing a visitor only when it was already close to leaving, humanity had more time to prepare and observe it during several stages of its journey. After the two earlier encounters, astronomers also understood that the first days were especially important. The orbit needed to be updated continuously. Older images had to be recovered. Small changes in brightness could help reveal the object's activity. Most importantly, the light from the gas around the nucleus had to be analyzed before the comet traveled too far away and became too faint. 3I Atlas showed relatively clear cometary activity. As it entered the region warmed by the sun, volatile substances within its ice began changing into gas. The escaping gas carried dust with it and created a faint envelope around the nucleus. To an ordinary observer, this might appear as nothing more than a vague glow without a clear shape. But to scientists, that gas was like a sample carried outward from the comet's interior by the comet itself. Humanity is not yet capable of sending a spacecraft toward an interstellar visitor immediately after its discovery. These objects usually move quickly, and the directions from which they will approach are not known in advance. Designing, launching, and guiding a spacecraft to pursue one within a short period would be an enormous challenge. In most cases, light therefore remains the only connection between Earth and material arriving from another star system. Light can carry far more information than its simple appearance suggests. When a molecule absorbs or emits particular wavelengths, it leaves behind a unique pattern in the spectrum. That pattern is like a fingerprint. By identifying lines and bands within the light, researchers can determine whether the coma contains water, carbon dioxide, carbon monoxide, or other compounds. The James Webb Space Telescope offers a special capability for this work. It is particularly effective at observing infrared light, which has longer wavelengths than the red light visible to the human eye. Many molecules in gas and ice leave strong signatures at infrared wavelengths. Webb can therefore detect features that may be difficult to find through ordinary visible light observations. Webb cannot see through the entire cometary nucleus or photograph every layer of ice hidden deep inside. What it detects is the light coming from the gas surrounding the object. But that gas originates from substances once preserved within the ice. When the sun causes the material to escape, part of the comet's internal composition is carried outward to a place where telescopes can read it. This is why the cometary activity of 3I Atlas is so important. If the object remained completely inactive and released no gas, astronomers would mainly be able to measure its orbit, brightness, and overall color. Once the ice becomes active, another source of information opens. The object not only reveals that it came from outside the solar system, it also begins to expose the conditions in the place where it was formed. The three interstellar visitors therefore present three different kinds of questions. Oumuamua confronted humanity with an object that was difficult to classify, was observed too late, and showed no obvious cometary activity. Borisov demonstrated that a comet from another star system could still have a familiar appearance, while also providing the first relatively clear opportunity to study gas escaping from an interstellar comet. 3I Atlas arrived at a time when our observing instruments had become more advanced and humanity was better prepared. Each encounter does not replace the one before it. They complement one another. Oumuamua showed that nature can create visitors more difficult to understand than humans might expect. Borisov demonstrated that comets resembling familiar objects are also formed around other stars. 3. Atlas offers the opportunity to investigate the isotopic composition and chemical history of interstellar material in greater depth. The most important point is not that there have been 3 objects. 3 remains an extremely small number compared with the vastness of the Milky Way. 3 encounters cannot describe the entire population of bodies wandering between the stars. But each object is a genuine sample from another planetary system, delivered close to us without humanity having to cross the distances between stars. They may have formed around different stars, within regions of different temperatures, and during eras separated by billions of years. They may once have occupied belts of ice, passed close to giant planets, or been thrown outward while their original star systems were still young. Although their precise origins may remain unknown, their material still carries traces of those places. For 3I, Atlas, the faint gas surrounding the nucleus becomes a doorway into a deeper story. Light passing through or emerging from that gas may reveal which molecules are escaping. The ratios between different forms of the same atoms may offer clues about the temperature at which the material formed. Its chemistry may even help scientists estimate during what period of the Milky Way's history the object was created. But before these measurements could be fully interpreted, a familiar question began appearing among the public. The first encounter with Oumuamua had sparked widespread discussion about whether an interstellar object might have an artificial origin. Although most research focused on natural explanations, the idea of technology arriving from beyond our solar system left a powerful impression on the human imagination. So when the third visitor was discovered, curiosity was not directed only toward its ice, gas, and dust. An old question quickly returned. Could an object traveling between the stars be the product of another civilization? The history of Oumuamua had cast a long shadow, and when 3I, Atlas appeared, questions about extraterrestrial technology quickly returned. Whenever an object from beyond our solar system is discovered, curiosity almost immediately extends beyond the boundaries of astronomy. This is not difficult to understand. Humanity has observed thousands of asteroids and comets belonging to our own planetary system, while the number of confirmed interstellar objects can still be counted on one hand. When there is so little data available for comparison, any unusual feature can create the impression that we are witnessing something entirely new. 3I, Atlas appeared under precisely these circumstances. It came from an unidentified place, carried material formed around another star, and traveled along a path from which it would never return. That origin alone was enough to make the object seem unfamiliar. But unfamiliar does not mean artificial. Just as an animal species never seen before does not necessarily have to have been created in a laboratory. An interstellar object is called interstellar only because its orbit shows that it arrived from the space between stars. The term says nothing about whether the object formed naturally or was manufactured, nor does it automatically turn every difficult-to-explain feature into evidence of a civilization. Yet this distinction often becomes blurred in the public imagination, especially after the long-running debates surrounding Oumuamua. When Oumuamua was discovered in 2017, astronomers had only a short period in which to observe it. The object did not produce the clear envelope of gas and dust expected from a familiar comet, yet its trajectory appeared to be affected by a small force beyond ordinary gravity. Its brightness also changed dramatically, suggesting that its shape might have been elongated or flattened. These features were not enough to prove an artificial origin, but they created a large gap in our understanding. In science, gaps in the data are usually filled with several competing hypotheses at once. Some studies propose that Oumuamua was a fragment rich in volatile ice, releasing gas too faint for telescopes to detect. Other models described it as a highly porous object, a fragment broken from a larger body, or a natural structure altered by interstellar radiation over a long period of time. There were also suggestions that it might have been artificial, perhaps a thin structure being pushed by the pressure of light. That final possibility attracted particular attention because it touched upon a question humanity has asked for a very long time. Could another civilization have sent objects across the space between stars? This is a valid scientific question when expressed as a hypothesis that can be tested. The problem arises only when a possibility is mistaken for a conclusion, or when a lack of data is treated as evidence in its favor. Failing to find an immediate explanation does not mean the explanation must involve extraterrestrial technology. Throughout the history of science, many phenomena were once considered unusual, simply because the available instruments or models were not yet good enough. The first radio signals detected from pulsars were surprising because they repeated with such extraordinary regularity, but they were later explained by rapidly rotating neutron stars. Unusual patterns of light from distant stars also often become better understood when additional observations are collected. Nature can create structures and behaviors that humanity has not yet learned to recognize. For this reason, unusual simply means that an object does not completely match known patterns, or that the current data is not sufficient to explain it. Moving from that point to the conclusion that it is artificial is an enormous step. To take that step, scientists would need positive evidence of technology, not merely features that are difficult to understand. An artificial object might leave behind certain testable signs. It could emit a clearly structured radio signal, change direction in a way that cannot be explained by gravity or escaping gas, reflect light like a manufactured surface, maintain an unusual temperature, or produce a sequence of deliberate accelerations. Not every sign would necessarily be present, but a scientific hypothesis must generate at least some predictions that can be compared with observations. When 3I, Atlas was discovered, similar questions quickly appeared. Some people focused on its speed, its direction of approach, its brightness, and the earliest estimates of its size. Information that was still uncertain during the initial stages was sometimes interpreted as evidence that the object was extraordinary. Each time new data arrived, the numbers were updated, and those changes could easily be misunderstood as a sign that astronomers had encountered something impossible to explain. In reality, this is how astronomical observation normally works. When a new object has been followed for only a short time, its orbit, size, and level of activity all carry significant uncertainty. Its apparent brightness depends not only on the size of its nucleus, but also on the dust and gas surrounding it. A comet with a small nucleus but a broad coma can still appear bright, until the light from the nucleus can be separated from the surrounding material. Estimates of its size may change considerably. Its motion also needs to be followed over many days. A small error in position, or an inaccurate assumption about the release of gas, can affect the earliest orbital calculations. As telescopes add more measurements, the model is adjusted. This is not evidence of concealment or contradiction. It is simply the process of turning an initial estimate into a more precise result. For 3I, Atlas, the most important question is whether its motion contains any sign that the object is controlling its own path. So far, there is no reliable evidence of this. Its trajectory can be explained well by the gravity of the Sun and planets, combined with the small forces that may arise as material escapes from the comet's surface. Escaping gas can create thrust without any kind of engine. When sunlight warms a region of ice, gas is released in a particular direction. The tiny reaction force from that flow can slightly alter the comet's speed, direction, or rotation. On Earth, such a force might seem almost insignificant. But in space, where friction is nearly absent and motion is measured over long periods, even a very small effect can be detected. A comet does not necessarily release gas evenly across its entire surface. Some regions may be covered by thick layers of dust, while others expose volatile ice. Cracks, depressions, and the object's rotation change which areas receive sunlight. As a result, gas sometimes escapes in separate jets, producing small changes in motion that may initially appear complicated. But complexity does not mean intention. A leaf carried by the wind may change direction many times without choosing its path. A block of ice in space can also have its motion altered by light, heat, and the gas it releases without requiring any kind of guidance system. In addition to its orbit, telescopes observe the gas and dust surrounding 3I, Atlas. The images show that it is not a completely inactive solid body. The object has a coma, the faint envelope of gas around its nucleus, as well as dust carried outward when different types of ice turn into gas. This activity increases as it approaches the sun, exactly as a natural comet would be expected to respond to heat. Light from the coma also reveals the presence of molecules commonly found in cometary material. These are not signs of manufactured metal, engine fuel, or an engineered outer shell. The observations are consistent with a mixture of ice, gas, and dust formed in a cold environment. Each telescope sees only one part of the story, but when data from many instruments is brought together, the overall picture becomes increasingly clear. Some observatories monitor the brightness and shape of the coma. Other instruments measure its spectrum in search of molecular signatures. Spacecraft and space telescopes can observe wavelengths that are absorbed by Earth's atmosphere. When independent sources of data all point toward cometary activity, a natural object becomes the simplest and most consistent explanation. This does not mean that science declares extraterrestrial technology impossible. Science rarely dismisses such a broad possibility on the basis of a single observation. Other civilizations may exist, and the search for technological signals remains a serious field of research. But a general question about life beyond Earth is different from a conclusion about one particular object. To identify 3I, Atlas, as a spacecraft, there would need to be evidence showing that a natural comet model could not explain the data, while an artificial model explained it better and produced new predictions that were later confirmed. So far, this has not happened. No communication signal has been confirmed. No deliberate movement has been detected. No artificial structure has been observed. There is no behavior that requires a control system to explain it. The absence of such signs does not prove with absolute certainty that no artificial element could possibly exist. Absolute certainty is rare in science. However, the best conclusion is not the most exciting one. It is the conclusion that explains the greatest amount of evidence while requiring the fewest unnecessary assumptions. In this case, a natural interstellar comet fits what the telescopes have observed. That explanation may be less dramatic than stories about a mysterious spacecraft, but it does not make the object ordinary. On the contrary, once the artificial explanation fades, another kind of strangeness begins to emerge. 3I, Atlas may be a comet, but it is not a comet formed within the environment of our solar system. Its molecules and isotopes carry traces from somewhere else, perhaps a place far more distant and ancient than its faint appearance suggests. A natural object does not need to be identical to the comets orbiting the Sunday. Other planetary systems may form from clouds of gas with different compositions around stars born during different periods in the history of the Milky Way. The temperature of the planet-forming region, the amount of radiation from the parent star, and early collisions can all leave traces within the ice. If the comets of our solar system are pages preserving the childhood of the sun, then an interstellar comet is a page from an entirely different book. It may contain familiar elements, but their proportions do not have to be the same. Water is still water, and carbon is still carbon, but subtle variations in atomic structure can reveal the conditions under which the material formed. This is where the unusual nature of 3I, Atlas, becomes truly meaningful, not because it moves like a machine, but because it carries a chemical history that does not belong to the region of space around us. Not because it sends a deliberate message, but because the molecules in its surrounding gas are unintentionally leaving behind the fingerprints of an unfamiliar planetary system. Science often begins by allowing several possibilities to remain open at the same time. When data is limited, cautious researchers should not dismiss a hypothesis too quickly, simply because it seems unusual, but neither should they elevate a possibility into fact merely because it captures the imagination. Each new observation strengthens some explanations while weakening others. For 3I, Atlas, the data concerning its coma, dust, gas, and response to the sun's heat continues to strengthen the comet model. Meanwhile, the spacecraft hypothesis has produced no unique confirmed signature of its own. The balance of evidence therefore points increasingly clearly toward a natural object. The early questions were not entirely useless. They encouraged scientists to examine the orbit carefully, search for signals, compare possible acceleration mechanisms, and observe the object across many wavelengths. Even a hypothesis that is ultimately unsupported can help identify the kinds of data that need to be collected. But once those tests have been carried out, the results must be accepted in the direction indicated by the evidence. The visitor passing through our solar system shows no reliable sign of being an artificial structure. It does not adjust its course to approach Earth. It sends no signal. It does not maintain a shape or temperature that requires technology. It simply responds to gravity, light, and heat, like a small celestial body rich in ice. Even so, the word simply can be misleading. An interstellar comet is the product of a very long sequence of events. Matter gathered within a cold cloud. A star formed. Dust grains joined together into larger bodies. Then a gravitational disturbance expelled the object from its original star system. Afterward, it drifted through the darkness between the stars until it happened to encounter the Sunday. No civilization needed to build it for that journey to be extraordinary. Nature accomplished it through gravity, temperature, and time. And time itself may have preserved, within the object's layers of ice, a story far older than Earth. As discussions of an alien spacecraft gradually faded, scientists turned their attention toward a quieter source of information. Not a deliberate radio transmission, but light separated into narrow bands. Within them, molecules leave absorption and emission signatures that are almost impossible to see with the human eye. Those thin lines do not create a dramatic spectacle. They do not announce that a civilization has arrived. But they may reveal the temperature at which the comet formed, the kinds of ice preserved within its nucleus, and the era in which its material first appeared in the Milky Way. Once the spacecraft hypothesis was no longer supported by the data, a deeper question emerged. What can light reveal about ice that no human being has ever touched? 3I. Atlas is moving too quickly and is too far away for humanity to send a spacecraft to collect samples within a short period of time. Its nucleus is also too small to appear clearly in images. Even so, scientists still have a way to study the material carried by this interstellar visitor. They observe the light emitted and reflected by the thin cloud of gas surrounding it. The James Webb Space Telescope carries out this work using a near-infrared spectrograph. Infrared light has wavelengths longer than the red light visible to the human eye. We cannot detect it directly with our vision, but many molecules in gas and ice leave especially clear signatures in this part of the spectrum. Webb cannot see through the surface or photograph the individual layers of ice buried deep within the nucleus. Instead, the telescope observes material released by 3I, Atlas as it approaches the Sunday. Sunlight raises the temperature of the surface. Some types of ice do not melt into liquid first, but change directly from a solid into a gas. This process is known as sublimation. The escaping gas carries tiny particles of dust and creates a faint cloud around the nucleus. This cloud is called the coma, which can be understood simply as a very thin region of gas and dust surrounding the comet's nucleus. The nucleus is the solid body made of ice, rock, and dust. The coma is not a stable atmosphere like the atmosphere of Earth. It is continuously produced as ice sublimates and then gradually spreads into space. This thin cloud of gas becomes a natural sample for telescopes to study. Webb does not need to touch the comet. It only needs to collect the light that has interacted with the molecules inside the coma. When light enters the spectrograph, it is separated into many different wavelengths. We can imagine this process as similar to white light passing through a prism and spreading into a band of colors. However, Webb's spectrum extends far beyond the colors visible to the human eye. Within that band of light are regions that appear brighter or darker. They form because each type of molecule absorbs and emits energy in its own particular way. Water leaves one pattern, carbon dioxide leaves another. Carbon monoxide and other compounds have signatures of their own. These patterns are like fingerprints because they allow scientists to distinguish between molecules, even though the molecules themselves cannot be seen directly. Compounds, such as water, carbon dioxide, and carbon monoxide, are often called volatile substances. This does not mean they always exist as gases. It simply means that they can turn into gas at relatively low temperatures compared with rock and metal. In the cold environment between the stars, they can remain frozen for extremely long periods. When an object approaches a star, heat begins releasing them. By measuring the fingerprints of light within the coma, scientists can estimate part of the composition of the active ice layers on 3I, Atlas. The results do not reveal everything contained within the nucleus. Material buried deeper may never have been exposed to the sun's heat, while the surface may have been altered by radiation and small collisions. Spectroscopy therefore opens only part of the archive. Even so, that information is extraordinarily valuable. Every escaping molecule was once preserved within material formed in another star system. When those molecules appear in the coma, they carry traces of the temperature and environmental conditions in the place where the comet was born. We can imagine 3I, Atlas, as a frozen archive that has drifted through darkness for an immense amount of time. The sun does not open that archive by breaking the entire object apart. The heat of sunlight releases only a small amount of material, like a thin vapor rising from a cold surface. Webb observes that vapor and reads the signatures preserved within the light. What matters is not only whether the object contains water or carbon. These elements are not rare in the universe. The true value lies in the proportions of different forms of the same element. Tiny differences in atomic structure can help scientists estimate the temperatures the material once experienced and how much it has changed since it first formed. Spectroscopy, therefore, does not produce a clear image of the interior of 3I, Atlas. It creates a chemical record. Every bright or dark line contributes a piece of information, and when many signatures are combined, the story of the object's origin begins to emerge. Within the thin gas surrounding the nucleus, Webb detected molecules familiar from natural comets. But among those signatures was an unusual detail. The water released by 3I, Atlas, did not have exactly the same proportions as water found in familiar comets within our solar system. It was still water, made of hydrogen and oxygen. However, some of the hydrogen within it was heavier than the most common form. The proportion was so high that it may preserve evidence of an extremely cold formation environment. Within that faint cloud of gas, Webb found a familiar form of water carrying such an unusual ratio that it may point toward a birthplace colder than any region near Earth. For most of its journey between the stars, 3I, Atlas existed in a cold and dark environment. Far from any star, the light was too weak to warm its surface significantly. Compounds that could easily turn into gas remained trapped within layers of ice, while dust and rock formed a crust around the material inside. That stillness began to change as the object entered our solar system. Even from a great distance, energy from sunlight reached its surface and gradually raised its temperature. The sun did not immediately break open this ancient storehouse of ice. It began opening the layers slowly, through heat. 3I, Atlas, contains several different types of ice, and they do not all respond at the same time. Some compounds can change directly from a solid into a gas at extremely low temperatures. Carbon monoxide and carbon dioxide belong to this group. They can begin escaping while the object is still relatively far from the sun, where water remains mostly undisturbed in the form of ice. As gas escapes from the surface, it passes through tiny openings and carries dust particles with it. That dust spreads around the nucleus, creating the faint cloud visible to telescopes. This is the coma, the extremely thin region of gas and dust surrounding a comet's nucleus. The coma is not a stable atmosphere like the layer of air surrounding Earth. Earth has enough gravity to hold most of its gases close to the surface for long periods. A small comet cannot do the same. As soon as gas escapes, it begins spreading into space, while newly released material continues replacing what is being lost. The coma is therefore always changing. Its shape, brightness, and composition depend on the object's distance from the sun, its direction of rotation, and which regions of ice are receiving sunlight. As 3I, Atlas, moves closer, the amount of energy it receives increases. Layers of ice that had previously remained inactive begin releasing material, making the cloud around the nucleus more visible. The escaping dust particles do not remain still around the comet. Sunlight and the stream of charged particles flowing from the sun gradually push them away. This can lead to the formation of a tail. A comet's tail does not necessarily trail directly behind the object along its direction of travel. It usually points away from the sun because light and particles from the central star are pushing the material outward. What humanity sees around 3I, Atlas, is therefore not the true shape of its nucleus. Most of the visible light comes from the dust and gas surrounding it. Beneath that faint cloud lies a much smaller body in which ice, rock, and dust remain bound together. The surface of this body may not resemble the material buried deeper inside. During its long journey through interstellar space, the outermost layer was exposed to cosmic radiation. This radiation consists of high-energy particles traveling through space, capable of breaking apart or rearranging molecules on the surface. Tiny collisions with interstellar dust may also have made the outer layer darker, harder, or chemically different from the more primitive material beneath it. Such a crust can cover the volatile ice below. In some places, gas may remain trapped until the temperature becomes high enough, or until pressure beneath the surface creates a fracture. Material can then escape through concentrated jets, instead of spreading evenly across the entire surface. Some of the gas in the coma therefore comes from ice near the surface. Other gas may escape through newly formed fractures, or from regions of ice exposed after the dust above them has been carried away. This causes the composition of the gas to change over time. A measurement taken far from the sun may reveal more carbon dioxide. Later observations, after the object has been heated more strongly, may show water playing an increasingly important role. These changes do not mean that the measurements contradict one another. Each observation is like looking into a different layer of the object. Different types of ice are released at different temperatures, and not every region of the surface receives the same amount of sunlight. As a comet rotates through space, it can bring different areas toward the sun in turn, causing the flow of gas to strengthen or weaken in a repeating pattern. This is why scientists need to observe 3I, Atlas at many different points in time. A single spectrum reveals only the composition of the coma at the moment of observation. A longer sequence of data allows them to identify which substances appear first, which become more abundant as the object approaches the sun, and whether new regions of ice are being exposed. Each episode of escaping gas is like a small page removed from the archive. It does not tell the object's entire history, but it reveals part of the material preserved within it. When many pages are placed together, scientists can build a more complete picture of the conditions in which 3I, Atlas, once formed. What is especially significant is that these layers of ice do not appear to have been continuously heated for long enough to erase every trace of their original state. Cosmic radiation may alter the surface, but deeper material remains protected by the layers surrounding it. In the cold environment of interstellar space, heat does not travel deeply with ease, and there is no powerful continuous source of light causing the compounds to evaporate. As the object approaches the sun, that long preservation begins to end, one layer at a time. Molecules that remained undisturbed for an immense period are released into the coma. They survive there only briefly before sunlight breaks them apart. The solar wind carries them away, or they spread so widely that they become too thin to detect. This brief interval creates a valuable opportunity for humanity. While the material remains locked inside the nucleus, telescopes can learn almost nothing about its composition. Only when heat causes the ice to sublimate do the molecules inside enter the light and leave their signatures in the spectrum. The sun therefore both changes 3I, Atlas, and helps humanity understand it. Every layer of ice that opens causes the comet to lose some of its material, but it also carries away a fragment of information from the past. That fragment may preserve evidence of a cold cloud, a disk of material surrounding a young star, or a distant region within the planetary system that gave birth to the object. Among the substances being released, water is especially important. Water is not unusual in comets, and detecting it is not surprising by itself. What is unusual lies within the extremely small details of those molecules. Most of the hydrogen in water exists in the familiar lightweight form, but some of the hydrogen in 3I, Atlas, contains an additional neutron, making it heavier than usual. The ratio between these two forms of hydrogen is high enough to make scientists reconsider the environment in which the ice formed. Among all the molecules being released, water carries the most. The water escaping from 3I, Atlas, is still made from the two familiar elements, hydrogen and oxygen. But when Webb analyzed the light from the gas surrounding the object, scientists found that the hydrogen in those molecules was not entirely like the form commonly found on Earth and throughout most of the material in our solar system. Hydrogen is the simplest element in nature. The nucleus of an ordinary hydrogen atom contains only one proton. A proton carries a positive electrical charge, and nearly all the atom's mass is concentrated within it. A much lighter electron moves around the nucleus. Hydrogen, however, also has another form known as deuterium. The nucleus of deuterium still contains one proton, so it remains hydrogen. The difference is that it also contains a neutron beside the proton. A neutron carries no electrical charge, but its mass is nearly equal to that of a proton. A deuterium atom is therefore almost twice as heavy as ordinary hydrogen. Deuterium is known as an isotope of hydrogen. Isotopes are different versions of the same element. They contain the same number of protons, and therefore retain the same chemical identity, but they have different numbers of neutrons. Carbon, oxygen, and many other elements also have isotopes of their own. In most water molecules, both hydrogen positions are occupied by ordinary hydrogen. If one of those positions is replaced by deuterium, the molecule becomes slightly heavier. If both are replaced, the result is a form of water commonly known as heavy water. This name can sometimes make it sound like a dense, dangerous liquid or a substance completely different from ordinary water. In reality, heavy refers only to the greater mass of the atoms within the molecule. Small amounts of deuterium occur naturally in water on Earth. What matters is not simply its presence, but how frequently it appears compared with lighter hydrogen. In nature, deuterium is far less common than ordinary hydrogen. Scientists therefore measure the ratio between deuterium and hydrogen, usually called the D to H ratio. This ratio can vary depending on where the material formed and the history of temperatures it experienced. In the water released from the ice of 3I, Atlas, deuterium appears with an unusually high frequency. This does not mean that all the water within the object is heavy water, nor does it mean that most of its hydrogen has become deuterium. It simply means that, among the enormous number of hydrogen atoms measured, there are significantly more deuterium atoms than are usually found in the water of familiar comets belonging to our solar system. This tiny difference at the atomic level carries an enormous meaning. It suggests that the ice of this interstellar visitor did not form under the same conditions as most of the material that created the comets orbiting our Sunday. The reason lies in the way chemical reactions occur at extremely low temperatures. Light, hydrogen, and deuterium behave in nearly the same way, but because their masses are different, they do not participate in every reaction with exactly the same probability. In deeply cold environments, this subtle difference becomes more pronounced. Certain reactions on the surfaces of cold dust grains tend to retain deuterium more effectively. Over time, deuterium becomes incorporated into water and other molecules at a higher proportion than existed in the original environment. This process does not require an unusual mechanism or a powerful source of energy. It unfolds slowly inside extremely cold clouds of gas and dust, where atoms and molecules settle onto the surfaces of tiny dust grains. Each grain of dust can be imagined as a microscopic foundation. On its surface, hydrogen, oxygen, and other atoms meet, form simple molecules, and then freeze in place. Over time, thin layers of ice accumulate around the dust grain. As many grains begin sticking together, they become part of larger bodies and may eventually help form a comet. If this process occurs in an environment cold enough, deuterium becomes preserved within the ice at a higher ratio. The amount of deuterium in water can therefore act as a trace of the chemical conditions in which the material once formed. This trace is not a precise thermometer in the ordinary sense. It cannot directly reveal the exact temperature on a particular day or at a particular location. But when compared with chemical models, it helps narrow the range of environments that may have produced the ice. In the case of 3I, Atlas, the high deuterium ratio suggests that its material passed through a period of deep freezing. That place was far colder than any natural environment on Earth's surface. Molecules moved slowly, many substances settled onto dust grains, and the reactions that enrich material in deuterium had enough time to take place. This does not necessarily mean that the entire object formed in a single moment. Comets are often products of several different stages. Some of their material may begin forming within a cold cloud before the parent star itself appears. Other material may be processed within the disk of gas and dust rotating around the young star. Ice grains from different regions may mix together before gathering into a larger celestial body. The deuterium ratio measured today may therefore be the result of an entire chemical history. It may record not only the place where the object finally came together, but also the cold environments through which its raw materials traveled before that happened. This record can also be altered. If ice is heated for a long time, molecules may escape, condense again, or react with the surrounding material. If a comet repeatedly passes close to its parent star, its surface layers may be reprocessed. Powerful collisions can also mix material from different depths. The fact that the unusual deuterium ratio can still be detected in the gas of 3I, Atlas therefore suggests that at least some of its material was never completely heated and transformed. Although the surface has endured radiation for a long time, the ice now being released appears to have preserved some of the chemical characteristics of its past. This is the first scientific secret opened by the gas surrounding the interstellar visitor. It contains more than water. That water also preserves a trace of the cold in which it once formed. A single water molecule cannot tell the complete history of a planetary system. But when trillions upon trillions of molecules carry the same unusual isotopic ratio, they create a pattern clear enough to compare. From that pattern, scientists can recognize that this material did not follow the same chemical path as the familiar comets of our own solar system. Even within the solar system, the deuterium ratio is not identical everywhere. Earth, comets, and icy bodies can carry different values. Scientists have long used these differences to study the origin of water on the planets and the way material once moved through the disk in which the sun formed. 3I. Atlas carries that method much farther. Instead of comparing objects that all formed around the sun, humanity is reading the signature of water from another planetary system. For the first time, An isotopic measurement may connect observations made near Earth with chemical conditions around a star that can no longer be identified. What is remarkable is that this information was not delivered through a deliberate signal. No message was transmitted, and no symbols were carved into the surface. The history of the object lies within the distribution of its atoms. A single proton or an additional neutron may seem like far too small a difference to carry any meaning. But in astronomy, differences this small are sometimes the things that survive the longest. The shape of a surface can change. Dust can be swept away. Fractures can open and close. But the ratios between isotopes within the ice can preserve traces of the formation environment across unimaginably long periods of time. A tiny drop of water can therefore carry the memory of a cloud that disappeared billions of years ago. It does not preserve an image of that place, but it retains the chemical conditions the molecules once experienced. It reveals that the material existed within cold deep enough for deuterium to be preserved more abundantly than usual. Water, however, answers only part of the question. It indicates that the formation environment was extremely cold, but it does not directly reveal when that environment existed. A cold cloud could have appeared during many different periods in the history of the Milky Way. To determine whether 3I, Atlas, is only slightly older than our solar system or formed when the Milky Way itself was still young, scientists need another independent trace. That trace is not found in hydrogen, but in another element that is also widespread throughout stars, planets, and living things. Heavy water reveals that 3I, Atlas, once existed in an extremely cold place. But to learn what era that place belonged to, scientists need another clock, one made from carbon. The unusual deuterium ratio in the water of 3I, Atlas, does more than reveal that the object once passed through a cold environment. When the observations are placed within chemical models, scientists can begin narrowing down the conditions required to produce such a signature. Current models suggest that the material carried by this interstellar visitor may have formed at temperatures no higher than about 30 Kelvin, equivalent to nearly -243 degrees Celsius. Kelvin is the temperature scale commonly used in physics and astronomy. Unlike the familiar Celsius scale, it begins at absolute zero, the lowest temperature matter can approach. So 30 Kelvin is not simply an extremely cold winter day. It describes an environment containing almost no warmth, where atoms and molecules move far more slowly than they do on Earth. At temperatures this low, many substances that would exist as gases in warmer environments can settle onto the surfaces of tiny dust grains. Interstellar dust grains are not like the familiar dust found inside a room. They are microscopic fragments of material, often containing silicates, carbon, and minerals that have been created or altered across many generations of stars. Within the dark regions of a cloud of gas, these grains act as surfaces where chemistry can take place. Hydrogen atoms, oxygen atoms, and simple molecules collide with them and become trapped. Extremely thin layers of material gradually cover their surfaces, much like frost forming on a cold window, but on a far smaller scale and within an environment more diffuse than any ordinary laboratory. A single dust grain may be no larger than a tiny fraction of a grain of sand. Yet atoms can still move slowly across its surface, encounter one another, and combine to form new molecules. Hydrogen and oxygen can help produce water. Carbon and oxygen can form other simple compounds. When the temperature is low enough, newly formed molecules cannot easily escape and remain frozen within the layer of ice. The cold does not stop every chemical reaction. It simply changes the way those reactions occur. Some processes become slower, while others gain an advantage because molecules remain on the surface long enough to meet one another. Under these conditions, deuterium can also be incorporated into water and other compounds at higher than usual proportions. Light hydrogen and deuterium behave almost identically in chemical reactions, but deuterium is heavier because it contains an additional neutron. At extremely low temperatures, this small difference in mass becomes more important. Certain reactions retain deuterium more effectively, causing it to gradually accumulate within molecules forming on the dust grains. Over time, the layers of ice grow thicker. Ice-coated dust grains collide and begin sticking together. At first, they form only very small clusters. After countless encounters, those clusters may grow into larger grains, pebbles, and eventually bodies massive enough to contribute to the formation of comets or other small celestial objects. 3I. Atlas may have begun through a quiet process like this. Before becoming a body of ice wandering between the stars, its material may once have existed as thin frozen layers covering countless dust grains. Those layers preserve traces of the temperatures at which they formed and were later gathered together as material within a young star system began to accumulate. One possibility is that this process occurred in the distant outer region of a protoplanetary disk. A protoplanetary disk is a disk of gas and dust rotating around a young star. Close to the star, temperatures are higher, and many forms of ice cannot survive for long. Farther outward, the starlight becomes weaker, the environment grows colder, and volatile compounds begin to freeze. In the outermost part of the disk, where the star provides very little heat, icy grains can remain almost undisturbed. This is a suitable region for the formation of comets and other small bodies rich in volatile substances. If 3I, Atlas, formed in such a place, its high deuterium ratio may preserve evidence of the enormous distance that once separated it from its parent star. There is, however, another possibility. Some of its material may have formed before the parent star had fully emerged. Stars are born within cold clouds of gas and dust. When one region of a cloud contracts under gravity, matter gradually concentrates at the center and creates a young star. The remaining material forms a rotating disk around it. Even before this stage, ice may already have accumulated on dust grains within the dark cloud. If that material later fell into the protoplanetary disk without being heated too strongly, chemical signatures from the original cloud could have survived. In this way, 3I, Atlas may carry both the memory of the planet-forming disk and the memory of the cloud that gave birth to its parent star. Current data does not allow scientists to choose confidently between these two scenarios. They cannot trace an individual water molecule backward to determine whether it formed before or after the star was born. What they have are isotopic ratios, the composition of the gas, and models describing how chemistry changes across different environments. Those models cannot perfectly recreate every detail of a star system that disappeared from view long ago. They are based on known reactions, the movement rates of molecules, radiation intensity, and temperature. When a model produces a deuterium ratio similar to the one observed, it suggests that the simulated environment may offer a reasonable explanation. The temperature value should therefore not be understood as a direct measurement taken at the birthplace of 3I, Atlas. No thermometer was ever placed inside its original star system. The temperature is inferred from the way atoms were arranged within the ice and from the conditions required to produce that arrangement. This chemical signature may also be the result of several overlapping stages. The material may have formed inside an extremely cold cloud, entered a warmer disk, and then moved outward again into a frozen region. The mixing of older and newer material may have produced the composition humanity observes today. This makes the origin of a comet more complicated than the image of a block of ice forming at a single location. It is more like a collection of particles that pass through several different environments before joining together as one object. Each particle may have carried part of its own history, but once they were assembled, they created a shared chemical signature. Although the exact location remains uncertain, one conclusion stands out. 3I, Atlas carries evidence of an unusually cold environment. This was not simply the cold the object experienced while wandering between the stars. The deuterium ratio indicates that low temperatures played a role in creating its molecules from a very early stage. In other words, the cold did more than preserve the ice. It helped shape the composition of that ice. It was within this deeply frozen environment that more deuterium became trapped, molecules settled onto dust grains, and slow chemical reactions produced the material that later became part of the comet. Over billions of years, the surface of 3I, Atlas, may have changed. Cosmic radiation affected its outer layers, small collisions created additional fractures, and its present journey near the Sun is gradually releasing material. Yet its isotopic signature shows that at least part of its earliest history has not been erased. This allows scientists to observe gas escaping today and draw conclusions about a region of space that existed long ago. There are no images of that cloud. No one knows where the parent star is now. But within a tiny drop of water, a slightly greater abundance of deuterium has preserved part of that ancient cold. This is what makes 3I Atlas so remarkable. It is not merely an object that became frozen in space. It is a product of chemistry that could unfold in this particular way only when the environment was cold enough, dark enough, and quiet enough for molecules to remain attached to tiny grains of dust. From nearly invisible dust grains, ice gradually accumulated. From thin layers of ice, larger bodies began to form. And in a distant region around a young star, a small celestial object may eventually have been born before being expelled from its planetary system and beginning its journey between the stars. Temperature, however, answers only the question of conditions. It tells us that the material formed in deep cold, but not when that cold environment existed. Frozen regions still appear throughout the Milky Way today, just as they existed in the distant past. To distinguish a comet only a few billion years old from an object that may have formed when the Milky Way was still young, scientists need to examine another signature. This signature reflects not only temperature, but also the way the chemical composition of the galaxy changed across many generations of stars. Temperature tells us only that 3I Atlas was created in the cold. The carbon signature begins to reveal when that cold existed. The deuterium signature in the water of 3I Atlas suggests that its material once formed in an extremely cold environment. But such cold conditions can exist in many places and during many different periods. To determine how ancient this interstellar visitor might be, scientists need another kind of clue. That clue lies in the carbon being released from its ice. Carbon is a familiar element on Earth. It is found in living organisms, in carbon dioxide gas, in rocks, and in many organic compounds. But not every carbon atom is exactly the same. Carbon can exist in several forms known as isotopes. Every carbon atom contains 6 protons in its nucleus. That number of protons is what defines it as carbon. Carbon 1,2 also contains 6 neutrons, creating a total of 12 particles in the nucleus. It is the most common form of carbon in nature. Carbon 1,3 still has 6 protons, but it contains 7 neutrons, making it slightly heavier than carbon 1,2. Carbon 1,3 is a stable isotope. It is not a dangerous radioactive substance, and it does not decay in the way often associated with carbon 1,4. The main difference between carbon 1,2 and carbon 1,3 is a single additional neutron. Yet that tiny difference can become an extremely valuable clue when scientists attempt to understand the origin of matter. Measurements of the gas surrounding 3I Atlas indicate that the ratio of carbon 1,2 to carbon 1,3 is higher than the ratio commonly found in material from our solar system. Put more simply, the object appears to contain relatively little carbon 1,3. Both forms of carbon are still present, but carbon 1,3 is less abundant when compared with carbon 1,2. This is not merely a random chemical characteristic. The isotopic composition of the Milky Way has not remained constant throughout its history. The galaxy has changed through many generations of stars, and each generation has helped transform the material from which the next generation would form. During the early universe, most ordinary matter consisted of hydrogen and helium. Heavier elements were not yet as abundant as they are today. Carbon, oxygen, nitrogen, and many other elements were created inside stars through nuclear reactions unfolding over millions or billions of years. A star can be imagined as an enormous furnace for transforming matter. During most of its life, it combines lighter nuclei into heavier ones. Stars with different masses and lifespans produce elements and isotopes in different proportions. As they age, stellar winds, expelled outer layers, or final explosions return some of that altered material to space. That material mixes into clouds of gas and dust between the stars. Later, new clouds collapse and form the stars, planets, and comets of the next generation. Every cycle changes the chemical composition of the Milky Way a little more. Later generations of stars are not born from exactly the same material as the earliest ones. They form in environments that have already been enriched with carbon, oxygen, iron, and many other elements. Certain isotopes also become more abundant over time because different types of stars and different lengths of time are needed to create and disperse them. Carbon, 1,2, can be produced relatively early inside many stars. Carbon, 1,3, depends more heavily on processes occurring within later stellar generations that already contain carbon and other heavier elements. Over time, the amount of carbon-13 inches the interstellar environment can therefore increase relative to carbon, 1,2. This process does not unfold evenly throughout the galaxy. Regions near the center of the Milky Way have experienced a different history of star formation from the outer regions. An area that once produced many stars may become chemically enriched more quickly than a quieter region. Gas can also move, mix, or enter the Milky Way from outside. The carbon ratio is therefore not a simple clock from which an exact age can be read directly. Even so, it carries information about the era and environment in which the material formed. If a celestial object contains relatively little carbon, 1,3, that may suggest that its raw material condensed within an environment that had not yet passed through many cycles of recycling by successive generations of stars. In other words, it may have formed when the Milky Way was younger and contained fewer heavy elements than it does today. Scientists refer to this changing composition of matter across generations of stars as the chemical evolution of the galaxy. This is not biological evolution. It is the history of how stars create elements, release them into space, and provide raw material for new stellar systems. To interpret the carbon signature of 3I, Atlas, researchers place its observed isotopic ratio into models that simulate the chemical history of the Milky Way. These models follow the rate of star formation, the types of stars that existed, the material they produced, and the way different isotopes accumulated over time. When the carbon composition of the interstellar visitor is compared with those models, the results suggest that its material may have condensed between about 10 and 12 billion years ago. This span of time lies almost beyond ordinary human experience. It is billions of years older than Earth and places the object's possible origin within a very early period of the Milky Way's history. This number is not a directly measured birth date. No rock from 3I, Atlas, has been returned to a laboratory for age testing, and no record reveals the exact moment when its first grains of ice came together. The estimate of 10 to 12 billion years is inferred by placing the isotopic ratio within models of how the galaxy's chemistry changed over time. This means that the result always carries uncertainty. The models must make assumptions about where the object formed, how quickly generations of stars enriched the surrounding environment, and how thoroughly the material was mixed. Changing those assumptions can shift the estimated age. The isotopic ratio itself also has a margin of error. Molecules in the coma are extremely sparse, the object is distant, and the collected light is faint. Scientists must separate the signatures of carbon 1,2 and carbon 1,3 from many other sources of interference. Instead of saying that 3I, Atlas, is certainly exactly 12 billion years old, it is more accurate to say that its present composition is consistent with the possibility that it formed roughly 10 to 12 billion years ago. Future studies may make the result clearer. Other teams may measure carbon in different molecules, examine additional isotopes of nitrogen or oxygen, and improve models of the Milky Way's chemical evolution. When several independent clues point toward the same era, the age estimate will become more reliable. New data could also cause the estimated range to be revised. Despite the uncertainty, the current measurement remains especially significant. In the past, the ages of interstellar objects were often estimated from their motion through the galaxy. Older objects tend to have experienced more gravitational interactions and may move differently from younger ones. Motion, however, provides only an indirect clue. Carbon offers another path. Instead of looking only at how the object is moving today, scientists read the composition of the material from which it was made. One method is based on its present journey, while the other is based on the chemical memory preserved within its ice. When these two lines of research support one another, the picture of an ancient object becomes more convincing. The carbon clock has no hands and does not count individual years. It works through the slow accumulation of isotopes within the Milky Way. Every generation of stars adds more material to space. Planetary systems born at different times receive slightly different mixtures. Those ratios become locked into their ice, rock, and gas, where they may survive for an extraordinarily long time. 3I. Atlas appears to carry a mixture belonging to a much earlier period than our solar system. The Sun and its planets formed about 4.6 billion years ago from material that had already passed through many cycles of recycling within the Milky Way. If this interstellar visitor truly condensed between 10 and 12 billion years ago, then it had already existed in some form for billions of years before the cloud that created the Sun began to collapse. At that time, there was no Earth, no ocean, no moon, and no living creature looking up at the sky. The atoms that would one day form the human body were still scattered through many generations of stars. Meanwhile, in some distant frozen region, the material of 3I, Atlas may already have begun settling onto dust grains and gathering into a small celestial body. Most of that history left no image behind. Humanity does not know what the object's parent star looked like, how many planets once orbited it, or exactly what expelled the comet from its original system. But its carbon ratio still preserves a faint indication that the material belonged to a younger Milky Way. This is the explanation behind the figure of 12 billion years often associated with 3I, Atlas. It is not a number chosen to make the object appear more mysterious. It comes from comparing its isotopic fingerprint with the chemical history predicted for the Milky Way by scientific models. The result is not a final verdict. Science still needs more data, more measurements, and more interstellar objects for comparison. But even with that caution, the possibility before us is remarkable. A small body of ice now passing through our solar system may have formed when our galaxy belonged to a very different age. Deuterium told the story of the cold. Carbon begins to tell the story of time. When these two signatures are placed beside one another, 3I, Atlas appears as a fragment of matter that may have formed within an extremely cold environment, poor in heavy elements during the youth of the Milky Way. If that estimate is close to the truth, 3I, Atlas was born before the Sun existed, and the Milky Way of that time was very different from the place we inhabit today. If the estimates based on isotopes are approximately correct, the material that formed 3I, Atlas may have come together between 10 and 12 billion years ago. To imagine such a span of time, we must travel far backward past the formation of Earth, past the moment when the Sun first began to shine, and into a young Milky Way that had not yet taken on the stable form we recognize today. The universe is currently about 13.8 billion years old. So saying that 3I, Atlas may have formed 10 to 12 billion years ago does not mean that it appeared immediately after the Big Bang. Billions of years still separate those two moments. During that interval, the first stars had already been born, lived out their lives, and returned the elements they created to space. Galaxies had also begun to form, collide, and change. 3I, Atlas, is therefore not a fragment left directly from the moment the universe began. It may have formed later, after the earliest generations of stars had produced enough carbon, oxygen, and other necessary elements to create ice, dust, and small celestial bodies. Even so, if the age estimate is correct, it still belongs to an era far more ancient than our solar system. At that time, the universe was passing through a period of intense star formation. Enormous clouds of gas were continuously collapsing under gravity, producing new stars at a faster rate than during most later periods. Many young stars gathered into clusters, illuminating broad regions of gas and rapidly changing the environments around them. Our Milky Way was not yet complete. It was not a stable spiral disk that had existed unchanged from the beginning. The galaxy grew by drawing in gas from its surroundings and merging with smaller systems of stars. Streams of material collided, clouds were compressed, and new generations of stars emerged. The young Milky Way may have been a more turbulent place than it is today. Brilliant regions of star formation existed beside dark clouds. Stellar explosions released energy and matter into space. Young star systems were often born closer together, allowing the gravity of neighboring stars to influence objects near the outer edges of each system. Even among these highly active regions, however, extremely cold environments still existed. Inside dark clouds, where starlight struggled to penetrate, gas and dust could cool. Around newly formed stars, the outer regions of disks of gas and dust also lay far enough from the central heat for many molecules to freeze. These may have been the places where the material of 3I Atlas first began to form. The Milky Way of that era had a different chemical composition from the galaxy we know today. In astronomy, the term heavy elements is commonly used for nearly every element heavier than hydrogen and helium. This differs from the way the phrase is normally used on Earth. Carbon and oxygen, although not considered especially heavy in everyday life, are still placed within this category by astronomers. Hydrogen and helium appeared very early in the history of the universe. Heavier elements were created mainly inside stars and during powerful events at the ends of stellar lives. Every generation of stars that lived and later released material into space made the interstellar environment slightly richer in heavy elements. When 3I Atlas may have formed, that enrichment process had not advanced as far as it had by the time the Sun was born. The Milky Way already contained carbon, oxygen, and many other elements, but their average abundance was still lower than it is today. The raw materials needed to create rocky planets, metals, and complex compounds were not yet as plentiful as they would become billions of years later. This does not mean planetary systems could not yet exist. Even in an environment containing fewer heavy elements, dust grains could still form. Carbon and oxygen could still combine into simple molecules. Water, carbon monoxide, carbon dioxide, and many other volatile substances could still freeze in regions cold enough to preserve them. Tiny ice-coated dust grains could collide and stick together. Over time, they could form larger structures, growing from small clusters into pebbles, and eventually bodies several kilometers across. Not all of this material would become planets. Some of it would remain within distant belts, where small icy bodies continued orbiting their parent stars. If 3I Atlas appeared in an environment like this, it may provide evidence that small, ice-rich bodies were forming very early in the history of the Milky Way. Such objects did not need to wait for the age of the Sunday. They may already have existed around far older stars, created from chemical mixtures different from the material in our own planetary system. This is one of the deepest meanings carried by the interstellar visitor. Comets belonging to our solar system: Tahwidi N12, Tahwidi 4 enter Sun, Tahwidi 4D, Tahwidi 4 6 billion years ago. They are ancient samples of our planetary system's history, yet they would still be far younger than the estimated age of 3I Atlas. No object formed within our solar system could directly preserve the conditions of a planetary system born 10 or 12 billion years ago. By the time the Sun formed, that era had already receded billions of years into the past. Most of the ancient matter in this region had been mixed, heated, and recycled through many generations of stars. 3I. Atlas may be bringing a chemical sample from that distant past close to us. It is not a perfectly untouched sample, because its surface has endured radiation, collisions, and an extraordinarily long journey. But the isotopes preserved within its ice may still reflect the chemical environment in which its original material came together. If the carbon ratio points toward an environment relatively poor in carbon, 1:3, while the water contains an unusually high abundance of deuterium, these two signatures may together indicate an ancient and deeply cold star system, formed within a Milky Way that had undergone fewer cycles of chemical enrichment than the galaxy has today. At that time, the sun did not exist. The cloud of gas that would eventually form our solar system may not yet have gathered. The atoms now contained within Earth were still scattered through gas, dust, or stars belonging to earlier generations. There were no oceans, continents, or living things in the region of space we inhabit today. Meanwhile, somewhere else in the Milky Way, an unfamiliar star may have been beginning to shine. Around it rotated a slow-moving disk of gas and dust, where tiny grains collided and accumulated. Close to the star, the heat made it difficult for ice to survive. But farther out, the cold allowed water and many other compounds to remain frozen on dust grains. Thin layers of ice gradually formed. Deuterium became preserved within some molecules at higher proportions. The carbon composition reflected the chemical environment of the Milky Way at that time. Ice-coated grains joined together and may eventually have created one of countless small celestial bodies around the young star. It is impossible to know which of those bodies became 3I, Atlas, nor can we look back through a telescope and identify that exact star system, because the stars have moved over billions of years and the object left its birthplace long ago. The place where it formed can be reconstructed only through the information that remains within its chemistry. That does not make the story any less meaningful. A subtle isotopic ratio can connect the present to an era when the Milky Way was still building itself. It suggests that the chemistry responsible for creating ice and comets did not begin only within relatively young planetary systems like our own, but may have been active during much earlier ages. A Milky Way poor in heavy elements was not an entirely empty galaxy. It already contained stars acting as furnaces for creating new elements. It already possessed cold clouds, dust grains, and simple molecules. It had enough material to form some of the earliest worlds, along with countless small fragments of ice in the outer regions of star systems. 3I, Atlas may be one of those fragments. It does not preserve a complete image of the young Milky Way, but it may carry a trace that younger objects could not. Within its water and carbon, humanity may be reading evidence of planetary formation that occurred billions of years before the sun appeared. From a tiny point of light in an astronomical image, the story therefore expands across nearly the entire history of the Milky Way. The orbit reveals that the object came from beyond our solar system. Heavy water points toward a deeply cold environment. Carbon suggests the era in which that environment may have existed. When these clues are placed together, the interstellar visitor becomes more than a comet passing by. It becomes a possible sample from a time when some of the earliest ancient planetary systems were beginning to form. But for a body of ice born within the young Milky Way to pass near Earth today, it first had to belong to a particular star system. There, it gathered within a disk of material, existed among other celestial bodies, and may have orbited its parent star for an extremely long time. Somewhere within that young Milky Way, an unfamiliar star may have been born beside a disk of ice and dust, and 3I, Atlas may be a surviving fragment of that disk. 3I, Atlas could not have formed within completely empty space. Like every comet, it needed a place containing gas, dust, ice, and gravity, where small pieces of material could gradually gather into a celestial body. The signatures in its water and carbon suggest that this environment may have been extremely cold and may have belonged to a distant era, but they cannot yet identify the exact star that gave birth to this interstellar visitor. What we can do is reconstruct a plausible setting based on the way planetary systems form. This is not a directly observed image of the birthplace of 3I, Atlas. It is a possibility consistent with its chemical composition and with what astronomy currently understands about comets. The story may have begun around a young star while it was still surrounded by a broad disk of gas and dust. This is known as a protoplanetary disk, meaning a region of material orbiting a newly formed star where planets, moons, asteroids, and comets can gradually emerge. The region close to the star is usually warmer. There, many forms of ice cannot survive for long, while rock and metal may become the main ingredients of the bodies taking shape. Farther outward, the star's light and heat gradually weaken. Water and other volatile compounds begin to freeze and coat tiny grains of dust. If the deuterium ratio of 3I, Atlas truly reflects its formation environment, its material may have existed within an extremely cold region of that star system. This could have been the distant outer portion of the protoplanetary disk, where a single orbit around the star took much longer and icy grains could survive without being heated continuously. There, ice-coated dust grains collided with one another. Most of the earliest collisions may have occurred slowly enough that the grains did not completely shatter. They could stick together through extremely weak electrical forces on their surfaces and then form larger clusters. This process did not happen through one sudden leap. It was a slow accumulation unfolding across countless encounters. From grains almost too small to see, the material gradually grew into tiny pebbles and then into larger bodies. Astronomers call these intermediate bodies planetesimals. Put simply, they are small celestial objects that serve as raw material for planets or remain behind as comets and asteroids. Some planetesimals continued colliding and merging, eventually helping build large planets. Others were broken apart. Many small bodies never became part of a planet and continued to exist within distant regions of their star systems. 3I. Atlas may have belonged to this final group. It may never have been incorporated into a large planet, deeply heated, or exposed to pressures strong enough to erase its original icy structure. Instead, it may have survived as a small body within a distant belt of ice. An icy belt is a region where many bodies of rock and ice orbit a star, broadly similar to the outer regions of our solar system. There is no need to assume that its parent system looked exactly like ours. The number of planets, their sizes, and the distribution of smaller objects may have been completely different. The only necessary feature was a region cold enough to preserve ice. There, the object may have spent a long period in relative quiet. It orbited its parent star, received very little heat, and existed among countless other small bodies. Its internal layers of ice continued preserving traces of the cloud and disk that created it. Young planetary systems, however, are rarely completely stable. During their early stages, large planets may change their orbits. They exchange gravitational energy with one another and with the smaller bodies around them. An icy object traveling along a stable path can be pulled onto a different trajectory if it passes close enough to a massive planet. This process is known as gravitational scattering. It can be imagined as a close encounter in space during which a planet's gravity changes both the direction and speed of a smaller object. The planet does not need to collide directly with the comet. A single passage at the right distance can give the object additional energy or remove part of its orbital energy. If it gains enough energy, the small body can be pushed farther away from its parent star. After one or several close encounters, it may exceed the speed required to escape the system. A body that once orbited a star then becomes a free object drifting between the stars. This is one plausible scenario for 3I, Atlas, but there is currently no evidence proving that its parent system contained a giant planet, nor can scientists determine how massive such a planet might have been. This is an inference based on a common mechanism capable of ejecting small bodies from planetary systems. A passing star could also disturb the outer region of a system. Young star systems often form within clusters, where many stars exist relatively close together. During the earliest period, the gravity of neighboring stars can alter the orbits of icy bodies near the outer edge, pushing some inward and throwing others away. If the parent star belonged to a binary system, the movement of its companion star could also destabilize distant orbits. Many natural mechanisms could explain the departure of a comet, but after billions of years, there is almost no way to determine with certainty which mechanism acted upon 3I Atlas itself. An even greater challenge is finding the star that created it. Stars do not remain motionless in the sky. They orbit the center of the Milky Way, move above and below the galactic disk, and respond to many different gravitational fields. Throughout its journey, 3I Atlas has also been gently influenced by stars, clouds of gas, and the overall structure of the Milky Way. A tiny difference in velocity, extended across millions or billions of years, can lead to an entirely different position. So even if the object's present orbit is measured with great precision, tracing that path backward across an enormous span of time produces ever-growing uncertainty. The parent star may still exist somewhere in the Milky Way. It may still be shining, accompanied by planets that settled into stable orbits long ago, with no visible sign that a comet was once thrown from the system. That planetary system may also have changed dramatically as planets migrated, collided, or were disturbed by passing stars. Another possibility is that the parent star has aged and entered the final stages of its life. If it was more massive than the Sun, it may have stopped shining long ago and left behind a stellar remnant. If it was smaller, it may still be alive. Current data does not allow scientists to choose between these possibilities. Saying that the parent system has disappeared would therefore go beyond what the evidence permits. What we know with greater confidence is simply that 3I Atlas is no longer bound to that star. Its birthplace may still exist, but it lies too far away in space and too deeply buried in the past to be identified through any simple route. That lost connection brings a quiet sadness to the story of this interstellar visitor. It carries material from one specific place, yet no longer has an address to which it can return. The water within its ice may have formed inside a particular cloud. Its carbon may reflect the chemical history of one region of the Milky Way, but the name of the star, the structure of its planetary system, and the exact location of its icy belt have all been concealed by time. Even so, 3I Atlas is not completely separated from its origin. It still carries the traces left behind by its parent system. Its formation temperature is preserved in the deuterium ratio. Its chemical era is suggested by carbon. Its cometary structure shows that it once gathered from ice, dust, and rock within a planet-forming environment. Perhaps its parent star once appeared within a brilliant star cluster in the young Milky Way. Around it, a broad disk of gas and dust extended outward, with planets growing in the inner regions and millions of small icy bodies occupying the distant edge. 3I Atlas may have been only one among countless such objects, too small to influence the system but durable enough to survive through time. For its first millions of years, it may have orbited the star without anything unusual occurring. Then the structure of the system changed. A giant planet migrated. Another star passed nearby, or a slow sequence of gravitational interactions pushed its orbit farther and farther outward. A violent collision was not necessary to begin its interstellar journey. Sometimes, a single close passage near a planet is enough to change an object's future forever. After that encounter, its old orbit no longer remained closed. Each passage carried it farther away until the gravity of its parent star could no longer force it to return. From that moment, it was no longer a stable member of the icy belt. The star that once illuminated its surface gradually shrank behind it. Any planets that existed disappeared into the darkness. The temperature fell, and the object entered the longest stage of its history, drifting freely between the stars. Humanity may never find the star system that gave birth to 3I Atlas. But not knowing the name of its home does not weaken its natural origin. Instead, it reveals how completely time and motion within the Milky Way can erase once obvious connections. The interstellar visitor does not need to carry a map. Its composition is already a kind of memory. Within its ice lies the cold of the outer region of a planetary system. Within its dust lies material that once orbited a young star. And within its present trajectory lies evidence that this bond ended a very long time ago. To become an interstellar visitor, 3I Atlas first had to escape the gravity of the star that created it. Some event transformed a fragment of ice belonging to one planetary system into a wanderer traveling through the Milky Way. Within a young planetary system, not everything is necessarily as stable as the quiet picture we often imagine. Planets are still growing, their orbits may be changing, and countless small bodies of rock and ice are continually being pulled onto new paths. Some objects fall closer to the star, some collide with one another, and others gain enough energy to leave the system forever. 3I Atlas may have begun its interstellar journey during a turbulent period like this. However, there is currently no data revealing exactly what expelled it from its home. What science can do is examine the natural mechanisms powerful enough to transform a comet that once orbited its parent star into a free-floating object within the Milky Way. One of the most common possibilities involves giant planets. Worlds with enormous mass create gravitational fields strong enough to significantly alter the orbits of smaller bodies passing nearby. The object does not need to collide with the planet. It only needs to come close enough for its direction and speed to be changed. This process is known as a gravitational energy exchange. The name may sound complicated, but it can be understood as an encounter in which the planet and the smaller object influence each other's motion. The giant planet changes very little because its mass is so great, while the small comet may gain or lose a substantial amount of energy. If it passes in one direction, the object may be slowed down and fall deeper into the star system. But if the encounter occurs along another path, the planet's gravity can accelerate it. The object approaches at a lower speed, swings around the planet, and departs faster than it was moving before. Humanity has used the same basic mechanism to guide spacecraft. A probe can fly close to a planet and change its speed without consuming a large amount of fuel. In nature, comets and asteroids undergo similar encounters, but no one chooses their trajectories for them. If 3I Atlas once passed close enough to a giant planet, it may have received the push it needed. Afterward, its new orbit would have carried it increasingly far from its parent star. If it had not yet gained enough energy, it might have returned and experienced another interaction. Each encounter would have continued changing its path until the orbit was no longer closed. The deciding factor is escape velocity. This is the speed an object must reach to leave a star's gravitational influence without being pulled back. While it remains below this threshold, the object still belongs to the star system, no matter how far away it travels. Once it crosses the threshold, however, its path opens into the surrounding space. There is no bright boundary marking the exact second when the object leaves its home. The star's gravitational pull weakens gradually with distance rather than ending abruptly. But in orbital terms, there comes a point when the object carries enough energy that it will never return. From then on, the parent star only continues shrinking behind it. Giant planets are not the only possibility. A passing star can also disturb the outer regions of a planetary system. Comets located extremely far from their parent star are held only by a relatively weak gravitational pull. If a neighboring star passes close enough, its gravity can alter the orbits of many small bodies. Some objects may be pushed toward the inner system. Others may be drawn farther outward and eventually escape entirely. The encounter between two stars does not need to be close enough for them to collide. In crowded regions, a single passage at the right distance can change the structure of an entire icy belt. This possibility is especially important within star clusters. A star cluster is a group of stars formed close together from the same cloud of gas. During the earliest stages, the distances between them may be far smaller than the present distance between the Sun and its neighboring stars. Gravitational encounters therefore occur more frequently. If the parent star of 3I, Atlas, was born within a crowded cluster, the outer region of its planetary system may have been disturbed repeatedly. Small icy bodies at the system's edge would have been especially vulnerable to being pulled onto new orbits because they were already far from the central star. Some objects may even have been transferred between two star systems. Many others may have been thrown directly into interstellar space. Binary star systems also create complicated environments. In such a system, two stars orbit one another. Their combined gravity can make distant orbits less stable. A comet entering the region influenced by both stars may undergo several accelerations and changes of direction before being expelled. There is no evidence proving that the parent star of 3I, Atlas, belonged to a binary system or a star cluster. These are simply natural paths capable of carrying a small object away from its home. Each is consistent with what astronomers have observed during the formation and evolution of planetary systems. The departure could also have occurred much later, after the parent star had grown old. During most of its life, a star keeps its planets and comets in orbit through its mass. But as it enters the final stages of its existence, it may expel some of its material and gradually lose mass. As the star's mass decreases, its gravitational hold on the surrounding objects also weakens. Distant orbits begin to expand. Planets may shift, while icy belts at the edge of the system become more vulnerable to passing stars, or to the influence of the remaining planets. An object that had remained stable for billions of years could suddenly enter a new sequence of interactions. It might pass close to a planet, become accelerated, and then escape the system. So 3I, Atlas, did not necessarily have to be expelled soon after it formed. It may have orbited its parent star for an extremely long time before some disturbance disrupted its old path. At present, there is no way to know which scenario truly occurred. Its chemical composition reveals that the object formed in the cold. Its current orbit proves that it no longer belongs to a particular star. But between those two moments lies a gap in its history that present-day observations cannot completely fill. Although the exact mechanism remains unknown, models show that planetary systems losing small bodies is not unusual. During the process of planet formation, large worlds do more than gather material. They also continually clear away and eject many fragments of rock and ice. Even our solar system may have lost an enormous amount of material in this way. As the giant planets change their orbits during the early stages, countless small bodies may have been thrown into the Sun, collided with planets, or escaped into interstellar space. This means that the Milky Way may contain an immense population of wandering objects. They produce no light of their own. Far from the stars, they are cold, dark, and almost impossible to observe. Most may drift for billions of years without ever coming close enough to a star for their ice to become active. Only a very small fraction happen to enter a region where humanity can detect them. When an object like 3I, Atlas, approaches the Sun, the light makes it brighter and releases gas. For a brief period, one member of this nearly invisible population emerges from the darkness. If countless interstellar objects are drifting through the Milky Way, the three visitors confirmed so far may represent only a tiny part of a continuous flow of material passing between star systems. Every star with planets may be both a birthplace of small celestial bodies and a source that ejects them into space. In this way, planetary systems are not completely isolated from one another. They may exchange material through journeys lasting millions or billions of years. A fragment of ice formed around one star may later pass close to another, carrying molecules and isotopes from its former home. 3I, Atlas, may be one rare example that humanity was fortunate enough to notice. It did not need to be sent intentionally. A chance gravitational encounter may have expelled it from its star system and delivered it into the shared space of the Milky Way. The moment it escaped its parent star's gravitational hold may not have been violent in any visible way. No explosion was required, and there was no glowing boundary. The object simply continued traveling farther after a change in direction, while retaining enough speed that it could never return. Behind it, the star that once warmed it gradually became smaller. Any planets that had shared the same system disappeared from view. The distance continued increasing until the parent star no longer looked different from millions of other points of light. From that moment, 3I Atlas entered a journey with no repeating cycle of return. It no longer experienced seasons or fixed closest and farthest points from its former star. Its motion was influenced only weakly by passing stars and by the overall gravitational field of the Milky Way. The push that carried it away from home may have lasted only a few hours, a few days, or a short series of interactions compared with the object's age. But the consequences of that disturbance continued through most of its remaining history. A comet that once belonged to an icy belt became a wanderer with no central star. Leaving a star system and surviving in interstellar space, however, are two different things. The push explains only how the journey began. It does not explain why the signatures of water and carbon are still present after a span of time nearly as long as the history of the Milky Way. Leaving its home required only a disturbance lasting for a short period. Preserving its chemical memory for billions of years demanded an almost entirely different kind of journey, one that was cold, dark, and marked by very little change. No one can reconstruct the exact path 3I Atlas traveled before it appeared near the Sunday. If the age estimated from its isotopes is approximately correct, that journey may have extended across most of the history of the Milky Way. During that time, the galaxy itself changed. Stars were born and disappeared, and new planetary systems continually formed from material left behind by earlier generations. Stars do not remain motionless against a fixed background. They all travel around the center of the Milky Way, each following its own orbit and responding to the galaxy's overall gravitational field. Large clouds of gas, clusters of stars, and distant stellar encounters can gradually alter the path of a small object. Each individual change may be almost insignificant, but when accumulated over millions or billions of years, these effects are enough to erase the trail leading back to the starting point. A tiny difference in velocity can carry an object into a completely different region of the Milky Way after enough time has passed. So even though the present trajectory of 3I Atlas can be measured with considerable precision, tracing it backward to one particular star is nearly impossible with any high degree of certainty. We know only that after leaving its parent star system, the object entered interstellar space. That environment is extremely sparse, but it is not completely empty. Between the stars, there is still gas, dust, faint light, and high-energy particles arriving from many directions. Most interstellar gas is so diffuse that only a small number of atoms may exist within a very large volume. Compared with the air on Earth, it is almost a vacuum. Yet over billions of years, even such a thin environment can leave an effect on the surface of an object. Tiny grains of dust sometimes strike a comet at high speeds. Each collision may create a microscopic crater, open a small fracture, or knock loose a fragment of material. No single impact is powerful enough to destroy the entire body, but together they can gradually make the outer layer rougher and increasingly different from the material buried deeper inside. Light from the stars also continues to reach the object, although it is extremely faint. Alongside that light are cosmic rays, high-energy particles created by powerful events in space, including stellar explosions. As they pass through matter, they can break molecular bonds or trigger new chemical reactions. This slow process of alteration is often known as space weathering. On Earth, wind, water, and changing temperatures gradually wear down the surfaces of rocks. In space, there is no rain or atmosphere, but radiation, cosmic rays, and countless small impacts can still transform the surface of a celestial body. The outer layer of 3I Atlas is therefore unlikely to remain exactly as it was when the object first formed. It may have become darker, harder, or filled with compounds produced through prolonged exposure to radiation. Some volatile molecules near the surface may have escaped. Others may have been broken apart and then recombined into new forms of material. These changes, however, do not necessarily extend throughout the entire object. Comets often have porous structures made from a mixture of ice, dust, and tiny empty spaces. This kind of material does not conduct heat efficiently. It can act like a natural layer of insulation, allowing the surface to react to its surroundings while the deeper interior changes far more slowly. In interstellar space, 3I Atlas did not remain close to a powerful source of heat for any extended period. It may have passed many stars, but most of those encounters would have occurred at distances too great for their light to significantly warm its interior. Between such passages were long intervals during which almost nothing changed. The deeper regions of the object may therefore have remained extremely cold. Low temperatures slow the movement of molecules and allow volatile substances to stay trapped within the ice. Water, carbon dioxide, carbon monoxide, and many other compounds may have survived across spans of time, during which almost no exposed material on Earth could have remained without being recycled. This does not mean that every molecule inside the object has remained completely unchanged. Cosmic rays can penetrate to a certain depth. Rare, larger impacts may expose older material. Fractures may open as temperatures change during occasions when the object passes near a star. But compared with a comet orbiting its parent star and repeatedly returning to warmer regions, an object wandering through interstellar space may avoid many cycles of heating. It does not experience regularly repeating seasons. It does not approach a powerful source of light every few decades or centuries. For most of its journey, the ice remains undisturbed beneath a dark crust. This prolonged stillness may help preserve its isotopic signatures. The deuterium within the water is not erased simply because the surface grows darker. The carbon ratio does not disappear merely because the object drifts through darkness. As long as most of the ice is not repeatedly heated, released, and condensed again, its original chemical memory has a chance to survive. What remains, however, is not a complete picture of its home. The ice does not preserve an image of the parent star, record the number of planets, or reveal exactly when the object departed. What survives consists only of subtle traces, an unusual isotopic ratio, a mixture of molecules, and a surface structure altered by time. We can imagine these traces as fragments of writing still visible on an extremely old page. Most of the story has faded, but a few symbols remain clear enough to show that the text was written during another era. Scientists cannot read the entire past of 3I Atlas. They can only assemble the surviving clues and construct the most reasonable story those clues allow. During those billions of years, many worlds may have been born and then changed completely. Continents formed, shifted, and disappeared. Oceans may have emerged on distant planets before freezing or evaporating. Many stars that once shone within the Milky Way reached the ends of their lives, leaving behind white dwarfs, neutron stars, or new clouds of gas. Meanwhile, a small body of ice continued traveling through dark regions. It had no awareness of passing time and no way to record the events unfolding around it. Yet the very absence of significant change helped transform the object into an archive. At certain times, 3I Atlas may have passed near cold clouds of gas. At others, it may have entered regions containing stronger radiation. Stars may have passed close enough to alter its trajectory slightly. But no available data allows humanity to identify any of those individual encounters. Any highly detailed account of the journey would therefore be only imagination. Science cannot say which stars the object passed, how long it remained within particular regions of the Milky Way. or whether it ever approached another planetary system. A more cautious conclusion is that its orbit experienced countless minor influences, while the memory of its path became increasingly blurred with time. Even so, its present surface may preserve some evidence of the journey. Dark layers, produced by radiation, may cover the ice beneath them. Small craters and fractures may reveal that many impacts occurred. When the sun began warming the object, those same fractures may have become escape routes for gas rising from better preserved regions inside. This helps explain why the coma does not necessarily reflect only the outermost layer. Gas can escape from pockets of ice beneath the surface as heat slowly reaches them. As pressure increases, the material finds paths through narrow fractures and carries dust outward with it. The molecules appearing within the coma may therefore originate in layers that were better protected from radiation. They may not be completely pristine, but they could preserve more information than the weathered outer crust. Each escaping jet of gas is like a small door opening into a deeper part of the frozen archive. That door does not remain in one place, nor does it stay open forever. As the object rotates, the region illuminated by the sun changes. One fracture may remain highly active for a time and then weaken. Another region may begin releasing gas. By observing the object at different times, scientists can compare the different layers of material being carried outward. If the isotopic ratios remain stable, that may suggest the signature is not confined to one small region of the surface. If the composition changes, it could reveal that the object consists of several layers with different histories. Yet even the best observations can sample only a tiny portion of the entire body. Most of the nucleus remains beyond view. The deepest layers may never be touched by the sun's heat during this passage. They will remain undisturbed as 3I, Atlas, moves away and becomes cold again. Perhaps molecules still exist there that have never been released since the object first formed. Perhaps some of the ice has survived through nearly the entire history of the Milky Way without ever being directly exposed to powerful light. But this remains a possibility, not something that can be confirmed through present observations alone. What can be stated with greater confidence is that a long journey through a cold environment created favorable conditions for preservation. Interstellar space is not a perfect container that keeps everything unchanged. It still alters the surface, exposing the object to radiation and dust. But compared with the heat near a star, these effects are usually slower and concentrated more heavily within the outer layers. The difference between the surface and the interior is therefore important. The surface tells the story of the journey, radiation, impacts, and space weathering. The deeper interior may tell the story of formation, the temperature, composition, and chemical environment in which the material was created. When 3I, Atlas, approached the sun, these two stories began to blend together. The outer layer was heated, fractures opened, and gas from inside passed through the weathered surface. The light collected by Webb carried traces of both the distant past and the encounter unfolding in the present. Humanity cannot separate every stage perfectly, but by comparing different molecules, isotopes, and observing periods, scientists can begin identifying which features may belong to the formation environment and which may have appeared later. This is why 3I, Atlas, should not be viewed as a perfectly untouched time capsule. It is more like an archive that has endured harsh conditions for an immense period while still preserving several important pages. Those pages do not reveal every detail, but they are enough to confirm that the object passed through a history very different from that of the comets orbiting our Sunday. 12 billion years, if that estimate is close to the truth, would not represent a period of complete stillness. The surface changed, the trajectory shifted, and some material may have been lost. But amid these gradual changes, the deeper ice may still have preserved atomic ratios established during a very early era. While large worlds experience volcanism, impacts, tectonic activity, and climate, a small body of material can sometimes preserve its memory for much longer. It has no molten interior, continually recycling its surface. It has no ocean dissolving its minerals. It has no thick atmosphere creating weather. Its simplicity makes it vulnerable, but it also allows some of its material to remain undisturbed for immense periods. Within the darkness of interstellar space, 3I, Atlas continued moving without knowing where it would eventually go. It had no predetermined destination. Weak gravitational fields gradually bent its path until a chance encounter carried it into the sun's region of influence. After billions of years without a powerful source of heat, the surrounding light began to intensify. The surface slowly warmed. The outermost layers of ice began to sublimate. Gas and dust appeared around the nucleus, transforming a dark body that had been almost impossible to see into a comet that could be observed from far away. The archive began to open only when a chance encounter brought 3I Atlas into the light of a star to which it had never belonged. After a journey that may have lasted billions of years through the darkness of interstellar space, 3I Atlas entered the region influenced by the Sunday. At first, the change was almost impossible to notice. Our star was still only a distant point of light, but the amount of energy reaching the surface had begun to increase. The frozen crust gradually absorbed heat, and molecules that had remained motionless within the ice began to move. The sun did not open this archive in a single moment. Heat traveled into the surface very slowly, and each type of ice responded at a different temperature. The compounds most easily transformed into gas became active first, even while the object was still relatively far away. Carbon monoxide and carbon dioxide could begin escaping under conditions in which water remained mostly locked in the form of ice. This process is known as sublimation. Instead of melting into a liquid, the ice changes directly into gas. In the near vacuum surrounding a comet, there is not enough pressure to maintain a stable layer of liquid water on the surface. Once the molecules receive sufficient energy, they leave the ice and travel directly into space. The first flows of gas may have passed through tiny openings and fractures in the crust. They carried not only volatile molecules, but also grains of dust lying on the surface. The dust and gas gradually spread around the nucleus, creating a faint region known as the coma. The nucleus of 3I Atlas may be only a few kilometers across, or perhaps somewhat larger, but the coma can extend across a vastly greater region. This is why telescopes often cannot clearly see the solid body at the center. What stands out in the images is the light reflected and emitted by countless dust grains and molecules surrounding it. A comet does not brighten because its nucleus begins producing its own light like a star. Sunlight strikes the dust and is reflected toward telescopes, making the coma easier to detect. At the same time, certain gas molecules absorb energy and then emit light at characteristic wavelengths. In this way, a small and dark object can become much brighter once it grows active. As 3I Atlas moved closer, the temperature of its surface continued to rise. Types of ice that had previously remained undisturbed began to sublimate. Water gradually took on a greater role in the comet's activity. Water molecules escaped, collided with dust grains, and helped produce stronger flows of gas. This change did not occur evenly across the entire surface. One region might be covered by a thick layer of dust and respond more slowly. Another might contain a fracture exposing fresh ice. As the object rotated, different areas turned toward the sun in succession, causing the amount of escaping gas to change over time. Every flow of gas represented the loss of part of the object's material. Molecules that had remained preserved within the ice for an immense period were now separated from the nucleus and dispersed into space. Some survived long enough to be detected by telescopes. Others were quickly broken apart into smaller components by sunlight. Dust continued drifting outward and could help form the comet's tail. The loss of material may sound like destruction, but for science, it is also the moment when information becomes available. While the ice remains deep inside the nucleus, it is almost impossible to observe directly. Humanity does not have a spacecraft waiting nearby to fly toward the object drill into its surface, and return samples. Only when the sun causes molecules to escape does the material inside enter a region that telescopes can examine. In this way, the sun becomes a natural key. It does not open the entire storehouse of ice or break the object into pieces. Its heat releases only tiny amounts of material, one layer at a time, from areas near the surface and from regions beneath fractures. Every escaping molecule is a very small part of what had once remained hidden. Sunlight travels through this gas and interacts with its molecules. Some wavelengths are absorbed, while others are emitted. By the time the light reaches a telescope, it carries subtle changes that the human eye cannot detect. A spectrograph separates the light into many wavelengths and turns those signatures into a chemical record. From this record, scientists identify water, carbon dioxide, carbon monoxide, and other volatile compounds. They cannot see individual molecules, but they can recognize entire groups through their fingerprints in the light. Lines and bands within the spectrum reveal which substances are present in the coma and the proportions in which they appear. What scientists read is more than a list of molecules. The ratios between them may reveal which types of ice are most active. Changes over time can expose different layers of material. Most importantly, the ratios between isotopes allow scientists to go beyond identifying composition and begin inferring the conditions in which the material formed. This is where the deeper secrets of 3I Atlas begin to emerge. Its water contains an unusually high abundance of deuterium, suggesting an environment of deep freezing. Its carbon indicates that the material may belong to an era when the Milky Way was younger and had not yet undergone as much chemical enrichment as it has today. These signatures existed within the ice for an extremely long time, but they became usable data only when the molecules were released into the coma. The object's interior is therefore not revealed through an image taken directly through the nucleus. It is inferred from material leaving the nucleus. Telescopes do not need to physically open the comet. They read the vapor flowing outward, much as someone might recognize the scent of a room even when its door is opened only slightly. But every time that door opens, the archive also loses part of itself. Molecules that escape will not return intact to their original positions. Dust is pushed into space. The surface changes. New regions of ice may be exposed, while other areas may become covered by material falling back down. Cometary activity is therefore both a measurement and a process of transformation. What scientists observe today is not exactly the same as the object's condition before it approached the Sunday. The act of making the object observable is inseparable from the changes caused by heat. This makes the timing of observations important. If 3I Atlas is observed only while it remains very far away, many types of ice may not yet be active, and the coma may not reveal its full composition. As it moves closer, water and other molecules become more visible. But if astronomers wait too long, the object will pass by, travel outward, and grow increasingly faint. Telescopes must therefore follow it through several stages. Every observation is a cross-section of the unlocking process. At first, the most volatile substances appear. Later, water takes on a greater role. As the object moves away, its activity gradually declines, and molecules that were once easy to detect become too diffuse to measure accurately. 3I Atlas does not stop for humanity to study it. It does not enter orbit around the sun, and it does not wait for a mission to be prepared. Its open path continues, carrying it through the inner solar system and then outward again. The observing window is only a very brief segment of a journey that may have lasted billions of years. As the distance increases, sunlight grows weaker, the surface temperature falls, the flows of gas become thinner, the coma contracts, and the brightness decreases. The ice no longer receives enough energy to continue sublimating strongly. The archive begins to close again. Some material has been opened and lost forever, but most of the nucleus may remain intact, continuing to carry layers of ice untouched by heat during this passage. When the object returns to interstellar space, those layers will once again settle into a state of cold stillness. Perhaps the molecules observed represent only a tiny fraction of everything 3I Atlas is carrying. Deeper layers may contain different ratios, compounds that have not yet been detected, or even older signatures. But there is no way to open the entire object using only light observed from a distance. What science receives is a collection of fragments of information. The orbit reveals its interstellar origin. The coma shows that it is an active comet. Heavy water points toward an extremely cold formation environment. Carbon suggests a very early era in the history of the Milky Way. Every measurement answers one question, while leaving clear limitations behind. Those limitations are what prevent the story from becoming an overly certain conclusion. 3I Atlas may have formed between 10 and 12 billion years ago, but that estimate depends on models. It may have come from an ancient planetary system, but its parent star has not been identified. Its ice may have been preserved remarkably well, but its surface has certainly undergone weathering. Even so, what has been revealed remains extraordinary. A small object passing through our solar system carried material from an environment humanity has never directly reached. Sunlight caused its molecules to escape. That same light then carried their signatures to our telescopes. In this way, a star far younger than the object itself may have helped humanity read the history preserved inside ancient ice. No drill touched the nucleus. No spacecraft landed on the surface. There was only heat, gas, and light. Yet those three simple elements were enough to transform a dark body of ice into a sample that could be studied from an enormous distance. The encounter will eventually end. The coma will fade, the molecules will disperse, and the object will continue toward the space between the stars. What remains will be preserved in spectra, orbital measurements, and the models built from them. 3I Atlas is only passing through, opening part of its memory before carrying the rest back into darkness. But the small portion it released was enough to raise the greatest question of the entire journey. After all these measurements, what is truly preserved inside 3I Atlas, and how certain can we be about its 1-2 billion year story? After all the measurements of its orbit, light, and surrounding gas, the mystery of 3I Atlas no longer centers on whether some hidden machine lies inside it. What telescopes have observed is far more consistent with a natural comet, a body of ice, dust, and rock, responding to the sun's heat through familiar physical processes. But as the artificial explanation recedes, another and much deeper secret begins to emerge. That secret is not an object hidden within the nucleus. It is information preserved within the very material from which the comet is made. To understand what 3I Atlas is telling us, we need to clearly distinguish between three different layers. Some things have been observed directly and are supported by the data with a relatively high degree of confidence. Other conclusions are inferred when those observations are placed within scientific models, and many questions still remain beyond humanity's ability to answer. The first well-supported fact lies in the orbit. 3I Atlas is not traveling along a closed path around the Sunday. Its speed and direction show that it arrived from beyond our solar system, passed through the gravitational region of our star, and will continue outward. It is not a native comet, completing an extremely long orbit. It is an interstellar visitor. The second well-supported fact lies in the activity observed around its nucleus. As the object approaches the sun, it releases gas and dust, creating a faint coma that extends far beyond the solid nucleus. This activity changes with the amount of heat the object receives, matching the way different types of cometary ice sublimate. No engine or guidance system is required to produce those jets of gas. Sunlight and the composition of the surface are enough to explain them. The spectrum of the coma reveals the presence of water and several other volatile substances. These compounds can remain frozen and undisturbed in a cold environment, then turn into gas once they receive enough heat. They do more than confirm that 3I Atlas is an active comet. They also carry material outward from the layers of ice, bringing it into a region where telescopes can read its chemical signatures. Among these clues, the water contains an unusually high ratio of deuterium compared with many familiar comets in our solar system. Deuterium is still hydrogen, but its nucleus contains an additional neutron. The high frequency of this heavier form of hydrogen does not transform all the water into some unfamiliar liquid. It simply shows that the process that created the ice occurred under chemical conditions different from those experienced by most material around the sunday. Measurements of carbon also reveal a notable difference. The ratio between carbon 1,2 and carbon 1,3 does not match the level commonly found in our solar system. The object appears to contain relatively little carbon 1,3, a stable isotope of carbon. This is not a dangerous feature or an anomaly suggesting artificial construction. It is a chemical characteristic that may reflect the era and environment in which the comet's raw material formed. These findings belong to the part of the story supported directly by the data, the interstellar orbit, the cometary activity, the gas and dust surrounding the nucleus, the volatile compounds, and the unusual isotopic ratios. They are signatures collected from light, although every measurement still carries uncertainties and limitations imposed by the instruments. The next step begins when scientists ask what conditions could have created those signatures. The high deuterium ratio is consistent with an extremely cold formation environment. Under deeply frozen conditions, certain chemical reactions preserve deuterium within water and other molecules more effectively. The ice of 3I. Atlas may therefore have begun forming inside a dark cloud or in the distant outer region of a protoplanetary disk, where light from the parent star provided very little heat. The carbon signature carries the story even farther. The chemical composition of the Milky Way has changed through many generations of stars. Stars create elements and isotopes, then return some of that material to space. Later generations form within environments that have become increasingly enriched. If an object contains relatively little carbon, 1,3, it may have come together during an earlier period, when the Milky Way had not yet experienced as many cycles of material recycling as it had by the time the Sun was born. When the carbon ratio is compared with models of the galaxy's chemical evolution, the results suggest that the material forming 3I, Atlas, may have originated between about 10 and 12 billion years ago. This is the source of the figure so often mentioned in the story of this interstellar visitor. But that age range is not a directly measured birth date. No one has a piece of the nucleus available for laboratory analysis. No geological layers have been counted, and there is no single clock pointing directly to an age of 12 billion years. The estimate is inferred by placing the isotopic signatures within models describing the chemical history of the Milky Way. The most cautious way to express the result is therefore that 3I, Atlas, may have formed roughly 10 to 12 billion years ago. Its true age may fall within that range, or the estimate may be revised as measurements and models improve. In the same way, describing it as a surviving fragment of an ancient planetary system is a reasonable inference rather than a directly observed image. Every comet needs an environment in which to form. Its material may once have existed inside a disk of gas and dust surrounding a young star, gathering in a distant region cold enough to preserve water, carbon dioxide, and other volatile compounds. A gravitational interaction may later have expelled the object from that system. A giant planet, a passing star, a binary star system, or changes occurring as the parent star aged could all have provided the necessary push. But no available data reveals which scenario actually occurred. The ice of 3I, Atlas, may also have avoided repeated heating throughout most of its history. While drifting between the stars, its surface was still exposed to radiation and small impacts, but the deeper interior may have remained at an extremely low temperature. This could have prevented some of the material from being completely reprocessed and allowed it to preserve chemical traces from the period when it formed. Even this possibility of preservation, however, must be understood carefully. 3 I, Atlas, is not a perfect time capsule. Its outer layers may have changed greatly. Cosmic rays have affected the surface. Interstellar dust may have created craters and fractures. Some volatile material may already have been lost. As it approaches the sun, heat continues changing the object again. What remains is not its entire past preserved without alteration. It is a collection of surviving fragments of information. From this point, the unknowns begin to widen. No one has identified the parent star of 3I, Atlas. Over billions of years, both the object and the stars have traveled around the center of the Milky Way. Small gravitational influences accumulated over time, making the path almost impossible to trace backward. The star may still be shining somewhere. It may also have changed dramatically or reached the end of its life long ago. No one knows how far from its parent star 3I, Atlas, formed. The deuterium ratio suggests an extremely cold environment, but that environment may have existed within a cloud before the star formed or in the distant outer region of a protoplanetary disk. The material may also have passed through several different environments before gathering into a comet. No one knows exactly what expelled it. A close encounter with a giant planet is a reasonable possibility, but it is not the only one. A passing star, motion within a star cluster, or changes in the mass of the parent star could also have destabilized the object's orbit. Its path after leaving home is also beyond our ability to reconstruct. 3I, Atlas may have traveled through many regions of the Milky Way, influenced by distant stars and clouds of gas. But there is no record of that journey. Its present orbit reveals only the tiny portion during which it entered the neighborhood of the Sunday. The deep nucleus remains another mystery. The gas escaping around the comet represents only material activated by heat during this particular passage. Deeper layers may contain slightly different compositions, may have been preserved more effectively, or may have experienced histories of their own. No spacecraft has drilled into the nucleus to examine them. Humanity also does not yet know how many objects like this are wandering between the stars. 3 confirmed visitors are not enough to represent the entire population. The Milky Way may contain an enormous number of dark icy bodies, most of which never pass close enough to a star to brighten and become detectable. None of these limitations reduces the value of 3I, Atlas. On the contrary, they reveal just how difficult a story science is attempting to read. From a faint point of light, humanity determined an interstellar orbit. From a thin cloud of gas, scientists identified water and carbon. From differences between isotopes, they inferred deep cold and an era that may lie billions of years beyond the age of the Sunday. So what has truly been preserved inside 3I Atlas? There is no reliable evidence of a machine hidden within the nucleus. There is no signal showing that the object is being controlled or was deliberately sent here. What lies within the ice is not a message written by a civilization. It is a chemical memory. It is a memory of the temperature at which the earliest molecules settled onto grains of dust. The cold allowed more deuterium to become preserved and left its signature within the water. It is a memory of the Milky Way's composition, when certain elements and isotopes were less abundant than they are today. The carbon ratio reflects a younger galaxy, where successive generations of stars were still gradually transforming the environment between them. It is a memory of another planetary system. Although the parent star has been lost, the ice still shows that somewhere there was once a region cold enough to produce small bodies rich in volatile material. It is a memory of how comets may have formed long before the sun was born. Ice-coated grains of dust collided and joined together, producing a body durable enough to survive through time. That memory is not written in words. It is written in the number of neutrons within atomic nuclei, in the ratio between light hydrogen and deuterium, and in the difference between carbon 1,2 and carbon 1,3. It exists within variations so small that the human eye could never see them directly. Humanity often expects great signs from space: a radio signal with a clear structure, an enormous construction blocking the light of a star, a spacecraft crossing the darkness between planetary systems. Such images easily attract attention because they resemble messages intentionally sent to us. But sometimes, the oldest message was never sent by anyone. A comet does not know it is carrying history. It did not choose a trajectory that would bring it close to Earth. It did not preserve its ice so that humanity might one day read it. Everything is simply the result of gravity, chemistry, and time. That is what makes the story more profound. The universe does not need intention in order to preserve memory. A cloud of gas can disappear, a star can drift away, and a planetary system can change beyond recognition, while traces of all three continue to survive inside a small fragment of ice. When that fragment passes near another star, heat releases a few molecules. Light carries their signatures to a telescope. From there, a story spanning billions of years begins to be read again. Not every line of that story remains intact. Much of it has been erased by time. No one knows the name of its home, the precise route it traveled, or its exact age. But the surviving signatures are enough to show that it does not belong to the era of our solar system. 3I. Atlas is therefore more than a comet passing by. It is evidence that planetary systems may exchange material across interstellar space. It shows that small bodies of ice can survive through enormous spans of time. And it reminds us that the history of the Milky Way is preserved not only within massive stars, but also inside dark objects that are almost impossible to see. This encounter will eventually end. As 3I, Atlas moves farther away, its surface temperature will fall. The flows of gas will weaken, the coma will fade, and the nucleus will once again become a tiny object in the darkness. The unopened layers of ice will continue their journey, carrying the parts of the story humanity never had the chance to read. But some traces will remain behind. They will exist within spectra, orbital measurements, and models that continue to be tested. From a brief encounter, humanity has received a glimpse of an era lying beyond every memory of Earth. And as 3I, Atlas continues moving away from the sun, most of its story will return to the darkness, waiting for another visitor to bring us one more fragment of memory from the distant star systems.